Welcome back to The Sleepy Scientist, where we gently unravel the universe, one peaceful idea at a time. If you're listening in bed, nestled under the covers, or just drifting into that soft, floaty space between thoughts, you're in the right place. Tonight, we're building a universe, quietly, carefully, and entirely from scratch. Now, I should warn you, this video may be a little too interesting. If it accidentally keeps you awake, I do apologise. But hey, if you're going to be wide-eyed at 1 in the morning, you might as well learn how galaxies form from invisible particles and equations. There are worse ways to lose sleep. If you enjoy videos like this, calming, thoughtful, and filled with cosmic curiosity, I'd love it if you gave this one a gentle like and maybe tapped subscribe. It helps more sleepy scientists like you find their way here. And if you feel like sharing, let me know in the comments where you're listening from and what time it is right now where you are. There's something lovely about imagining minds all around the world drifting off to the same stars at slightly different hours. Now take a deep breath, let your shoulders soften, let your mind slow to the pace of starlight, and let's begin exploring how, with just the right rules, a bit of code, and a great deal of patience, we might just build a universe. This video is for educational and entertainment purposes only, and is not intended to be medical advice. Imagine you're handed a blank canvas, not made of paper or pixels, but one filled with possibility. Now imagine painting not with brushes, but with equations. Instead of trees or skies, you're shaping galaxies, stars, dark matter, and time itself. That's the spirit behind a scientific simulation. At its heart, a simulation is an attempt to recreate the workings of the universe inside a machine. Not in the science fiction sense of plugging into the matrix, but in the very grounded, very real sense of using known laws of physics to model what we believe is happening out there, often billions of light years away. When scientists talk about simulations, they're not just talking about computer-generated imagery or something visually impressive for its own sake. A scientific simulation is a deeply mathematical experiment, an artificial version of the universe where researchers can test their ideas. It allows them to tweak variables, rerun histories, and see how different ingredients might influence the unfolding of galaxies, the birth of stars, or the shape of cosmic filaments. It's a kind of sandbox for reality, and while it might sound abstract, it's one of the most powerful tools modern cosmology has. Now, let's make something very clear. A simulation is not a photograph of the universe. It's more like a sketch drawn from memory, only the memory belongs to the equations of physics. Every single object in a simulation, from swirling galaxies to dark matter halos, is generated from a series of rules. These rules are based on our best understanding of how gravity behaves, how gas flows, how matter interacts over vast stretches of space and time. But instead of running these rules on a chalkboard, scientists run them on supercomputers, sometimes for days or even weeks. Of course, the word simulation carries different meanings in different contexts. In entertainment, simulations are used to create lifelike visuals for movies or video games. A digital wave crashing on a beach in a film might look real, but it's designed primarily for aesthetics. It doesn't need to obey the precise rules of fluid dynamics, just to convince the eye. Scientific simulations, by contrast, are judged not by how pretty they look, but by how closely they behave like the real thing. If a simulated galaxy spins too fast, forms too many stars, or collapses in ways that defy observation, the simulation is considered flawed, no matter how stunning the rendering. This is what makes scientific simulations so fascinating. They straddle a strange line between art and science. On the one hand, they require imagination. Someone has to decide which forces to include, how to represent time, how to model gas or gravity. On the other hand, they are tightly constrained by data. Observations from telescopes, satellites, and particle detectors set the boundaries for what the simulation can get away with. It's a bit like trying to write a symphony while only being allowed to use a limited set of notes. There's creativity, but it's boxed in by the known universe. To build even a basic cosmological simulation, scientists start with a kind of artificial Big Bang. A cloud of particles, usually millions or even billions of them, is distributed across a virtual space. Each particle doesn't represent a single atom or planet, but rather an enormous chunk of matter, often the size of a small galaxy. From there, the rules of gravity and expansion take over. Time is stepped forward in tiny increments, sometimes fractions of a million years at a time. With each step, the computer calculates how every particle moves in response to the others. Over time, patterns begin to emerge. Clumps of matter form, filaments stretch across space, and voids open up. These structures start to resemble the large-scale web of galaxies we see in the actual universe. You might be wondering, if simulations start with a made-up universe, how do we know they tell us anything real? The answer lies in comparison. Scientists compare their simulated universes to the actual cosmos, using data from galaxy surveys, background radiation measurements, and gravitational lensing. If the patterns match, if the simulated galaxies cluster in the same ways, if the voids are similarly empty, then confidence in the model grows. If not, scientists go back, tweak the inputs, adjust the assumptions, and try again. But here's the trick. Even the best simulation is only as good as the physics it's based on. If there's some key force or phenomenon we don't yet understand, like the true nature of dark matter or the detailed behaviour of magnetic fields, then that gap will show up in the simulation. It's like trying to bake a cake without knowing you've forgotten the sugar. The cake might still rise, but it won't taste quite right. And sometimes, the missing ingredient isn't just missing, it's completely unknown. That's where simulations become more than tools. They become a way to test our ignorance. When a simulation fails to match reality, it tells us that our understanding of the universe is incomplete. That's not a failure, it's a clue. A broken simulation might suggest that dark matter isn't behaving as expected, or that early star formation was more chaotic than we thought. By poking and prodding these digital universes, scientists aren't just playing with code, they're running experiments that are otherwise impossible. Consider this. We cannot rewind the universe and watch it evolve again under slightly different conditions. But with simulations, we can do exactly that. Rerun cosmic history with a different set of parameters, like a director filming a second take. What if gravity was just a little stronger? What if there were fewer black holes? What if the early universe was slightly smoother or more lumpy? Each simulation is a what-if machine, a chance to explore possible paths that might explain our present. And although these digital universes live entirely inside computers, they often feel strangely alive. Over time, simulated galaxies form arms, collide, merge, and give birth to stars. They evolve in complex, sometimes unpredictable ways. When researchers observe these behaviours, they're not just looking at pixels, they're watching the consequence of real physics, expressed in code. There's a quiet magic in that. It's important to remember that not all simulations aim for grandeur. Some focus on much smaller scales, simulating a single supernova or a clump of gas swirling into a black hole. Others zoom in on planet formation, turbulence in interstellar clouds, or even chemical processes in star nurseries. Each of these is a kind of focused lens, offering insight into a tiny corner of the cosmic puzzle. And it's not just astrophysics. Simulations are used in every corner of science, from modelling earthquakes to predicting weather patterns, to testing theories about climate, disease spread, and quantum behaviour. What unites them is the underlying principle: build a world out of math and see what it does. So when scientists talk about a simulation, they're not talking about an illusion or a trick. They're describing a carefully crafted mirror, a reflection of what we think the universe might be doing, built not from glass but from gravity, geometry, and time. It is, in a way, a kind of dreaming. Only instead of dreaming in images, we dream in equations. And somewhere inside those dreams, galaxies begin to turn. To build a universe, you need ingredients, not just stars and gas and dark matter, but the fundamental pieces of reality itself, the scaffolding upon which everything else is hung. Before you can simulate galaxies, you have to define what a galaxy is. Before you can model gravity, you have to decide how mass behaves. And before any particle moves a pixel, you need a rule book. That rule book is physics, and its language is mathematics. At the most basic level, a simulation begins with particles, but not particles in the sense of atoms or molecules. In cosmological simulations, each particle is more like a package deal, a simplified chunk of matter that represents an enormous amount of real mass. One of these particles might stand in for a dwarf galaxy, or a sprawling cloud of gas 1,000,000 light-years across. It's not trying to capture every atom, it's trying to stand in for the large-scale behaviour of that mass in space. These particles don't actually look like anything. They're just numbers, coordinates in a three-dimensional grid. Each has properties like position, velocity, temperature, and sometimes chemical composition. These values change as the simulation progresses, depending on how the particles interact with each other and respond to forces. In the end, the goal is to track the evolution of structure, where things go, how they clump, what forms, and when. But particles alone are useless without forces acting on them. And in the cosmic arena, there are a few headliners. Gravity is the big one. It's the force that sculpts the large-scale structure of the universe, pulling matter together over billions of years. It causes galaxies to form, clusters to merge, and dark matter to shape the invisible scaffolding that holds everything in place. In simulations, gravity is handled through Newton's laws, or in some cases more advanced formulations like general relativity, though that's usually reserved for specialized models, since it's incredibly demanding to compute. Most of the time, simulations calculate gravitational forces between particles using Newton's law of universal gravitation. The force between two particles is proportional to their masses and inversely proportional to the square of the distance between them. It sounds simple enough, but when you have billions of particles, the number of interactions explodes. Calculating every force between every particle becomes a titanic mathematical task. To make things manageable, simulations use clever shortcuts. One common method is called the tree algorithm. Instead of calculating every interaction individually, the simulation groups distant particles together and approximates their collective gravitational pull as a single force. It's like treating a distant galaxy cluster as one giant blob, rather than 1,000,000 individual galaxies. This dramatically reduces computation time while still maintaining accuracy where it counts. Then there's electromagnetism. While gravity dominates at cosmic scales, electromagnetic forces are essential for modelling how gas behaves. Hot gas clouds emit radiation, cool down, and collapse. Magnetic fields can shape the motion of charged particles, influence star formation, and stir turbulence in nebulae. In galaxy-scale simulations, electromagnetism is often simplified, but in smaller, high-resolution models, say, of star-forming regions, it becomes crucial. Simulations track how gas flows, cools, and compresses under pressure, allowing stars to emerge from collapsing clouds, like sparks from a smouldering ember. Another important player is hydrodynamics, the physics of fluids. In space, gas behaves like a fluid, especially when it's hot and moving through gravitational wells. Simulations use mathematical techniques to model fluid motion, including how shock waves form, how pressure builds, and how turbulence spreads. One common method is called smoothed particle hydrodynamics, or SPH. Instead of solving equations on a fixed grid, SPH treats gas as a collection of fluid-like particles whose properties are averaged over their neighbours. It's an elegant approach that allows simulations to handle messy, complex flows without too many rigid constraints. Let's not forget about dark matter. It's invisible, untouchable, and completely non-luminous, but it makes up the vast majority of mass in the universe. Simulations include dark matter as its own kind of particle, subject only to gravity. Since it doesn't interact electromagnetically, dark matter particles pass through each other without resistance, yet they still clump and collapse under gravity, forming vast halos that act as the gravitational anchors for galaxies and clusters. Dark energy, on the other hand, is a subtler player. It's not included in the form of particles, but as a modification to the expansion rate of space. Simulations incorporate dark energy by adjusting the cosmological parameters that define how space stretches over time. This affects the timing and scale of structure formation, influencing how quickly matter collapses and how spread out the universe becomes. Now all of this, particles, forces and energy, needs to be organised within a mathematical framework. That's where equations come in. Every force and interaction must be written out as a set of equations that the computer can solve over time. These aren't simple formulas, they're partial differential equations, often non-linear, coupled and unstable. They describe how things move, heat up, cool down, clump together, or fly apart. To simulate time, the computer breaks it into small intervals, tiny ticks of a cosmic clock, and calculates the state of the universe at each step. The choice of time step is crucial. Too large, and the simulation becomes inaccurate or unstable. Too small, and the run takes forever. It's a balancing act, and scientists spend considerable effort tweaking these settings to make sure the simulation runs smoothly without sacrificing accuracy. Underneath it all are the constants of nature, the speed of light, the gravitational constant, Planck's constant, and so on. These numbers are woven into every calculation, setting the scale for how energy flows, how mass curves space, and how particles behave. They're the dials on the cosmic mixing board, and changing them, even slightly, would lead to a universe that looks radically different. But even with all this machinery, there are still approximations. No simulation is exact. Some processes, like the behaviour of individual stars or the chaotic interactions in a dense galaxy cluster, are too complex to model directly. Instead, simulations use subgrid models. These are simplified rules that stand in for unresolved physics. For example, instead of modelling every supernova in detail, a simulation might inject a fixed amount of energy into the surrounding gas whenever a star-forming region hits a threshold. It's a bit like using shorthand to sketch a scene instead of painting every brushstroke. These subgrid models are often where the art of simulation comes in. They must be carefully calibrated to match real observations, and small changes can lead to big differences in the final outcome. It's one thing to simulate gravity. It's another to model the chaotic ballet of starlight, turbulence, chemical reactions, and magnetic feedback in a galaxy's heart. Still, even with all their complexity, simulations are fundamentally built from a handful of concepts: particles, representing mass and energy; forces, describing how those particles interact; equations, telling the system how to evolve; and time divided into a series of carefully measured steps, pushing the universe forward from one moment to the next. It's all very abstract until you see the results. Then suddenly, from these cold mathematical bones, a universe begins to grow. Galaxies spiral, clusters collide, voids deepen. And out of the equations emerges something astonishingly lifelike. A universe, made not of stars and atoms, but of code. It's a quiet kind of miracle, not a universe created by a divine hand, but by understanding. A simulation doesn't just mimic reality, it reflects our ability to describe it, and while it may not capture every detail, it shows just how far our minds can stretch when we start with the simplest of tools and ask them to build a cosmos. Once upon a time, not so long ago in cosmic terms, the idea of simulating an entire universe was something out of science fiction. Computers were bulky, slow, and wildly underpowered compared to today's sleek machines. But curiosity, as it so often does, outran technology. In the mid-20th century, a small number of ambitious scientists began asking a very big question. What if we could model the structure of the universe on a computer? Now, of course, they weren't imagining full 3D star fields or visual effects worthy of a space documentary. What they had in mind was simpler, just numbers on a grid, really. They wanted to take the equations that described gravity, mass and expansion, and see what happened if you let them play out in a digital space. It was like trying to build a sandcastle using only a teaspoon and a spreadsheet, but the vision was there. One of the earliest attempts came in the 1960s, when scientists started experimenting with simulations of how galaxies cluster under gravity. At the time, they could only manage a handful of particles, dozens at most, sometimes fewer than 10. Today that might seem laughable, but in context it was revolutionary. For the first time, researchers could watch gravity unfold step by step, not just through equations scribbled on chalkboards, but in the behaviour of moving particles on a screen. It was crude, yes, but illuminating. By the 1970s, computers had improved just enough to allow slightly more ambitious projects. Scientists like Sverre Erseth and his colleagues began running what were called n-body simulations, models in which particles interact gravitationally with each other. The n simply stands for the number of bodies involved. Early n-body simulations still only used a few hundred particles, but even that was enough to spot something interesting. Matter doesn't stay evenly distributed. Given enough time and gravity, it clumps. It forms filaments, knots, and voids. Even without any fancy physics, the large-scale structure of the universe begins to emerge from simple gravitational rules. Of course, these simulations didn't include gas or stars or dark energy. They were purely gravitational and entirely Newtonian. But they hinted at something deeper, that the vast and seemingly chaotic structure of the universe could arise naturally from initial conditions and simple forces. It was the first whisper that the universe might be a self-organizing system, and that its story could be told in code. Then came the grids. To simulate the universe on a larger scale, researchers needed a way to organize their calculations. One approach was to divide space into a regular three-dimensional grid, like a stack of invisible cubes, and calculate how mass and energy move from one cell to another over time. These grid-based models were more rigid than particle simulations, but they had an advantage. They allowed scientists to solve the equations of fluid dynamics more efficiently. Gas, after all, flows through space, compresses, expands, and radiates. A grid gave it somewhere to go. By the 1980s, cosmological simulations were growing in both size and sophistication. Researchers began to combine grid-based fluid models with n-body gravity solvers, creating hybrid systems that could simulate both dark matter and gas. These were still primitive by modern standards, but the results were eye-opening. For the first time, digital universes began to show something that looked like the cosmic web. Clusters of matter connected by thin, thread-like filaments, with vast empty spaces in between. These simulations suggested that galaxies don't form in isolation, but as part of a larger interconnected structure. The universe wasn't just expanding, it was sculpting itself. But to really simulate structure formation, something was missing. Dark matter. At the time, dark matter was still a relatively new and mysterious concept. Astronomers had noticed that galaxies rotate too fast for their visible matter alone to hold them together. Something unseen was providing extra gravity. The solution was dark matter, an invisible substance that doesn't emit or absorb light, but tugs on everything with its mass. Once researchers started including dark matter in their simulations, things changed dramatically. Dark matter behaves differently from ordinary matter. It doesn't clump into stars or radiate energy. Instead, it moves through space more like a ghost, only interacting through gravity. In simulations, it forms sprawling halos, spherical regions where dark matter is densest. Galaxies, it turns out, tend to form within these halos, like pearls nestled in invisible shells. The discovery of this structure was a major turning point in cosmological modelling. It gave simulations a backbone, something to hang galaxies on. As computing power continued to grow through the 1990s, simulations began scaling up. Researchers could now simulate millions and eventually billions of particles. These particles represented both dark matter and gas, allowing scientists to study how the two interact. The results were mesmerizing. Massive filaments of dark matter connected galaxy clusters like cosmic highways. Shock waves rippled through gas clouds. The large-scale structure of the universe began to look startlingly familiar. Not just a theoretical model, but a genuine match to what astronomers were seeing through telescopes. One important development during this time was the shift from idealized simulations, those with carefully controlled initial conditions, to more realistic, observationally anchored models. Scientists began using data from the cosmic microwave background, the faint glow left over from the Big Bang, to set the initial density fluctuations in their simulations. These tiny differences in temperature and density acted as seeds from which galaxies and clusters would grow. It was as though the simulation was being handed a real baby photo of the universe, and then asked to predict what that baby would look like 13 billion years later. The phrase universe in a box became a popular way to describe these efforts. A simulation would define a volume of space, a cube, perhaps 100 million light-years across, and populate it with virtual matter. The simulation would then evolve this cube over billions of years, step by step, according to the laws of physics. Each particle's movement would be calculated, each interaction noted. The goal wasn't to simulate the whole universe, but a statistically meaningful chunk of it, enough to capture the range of structures we see in reality. These boxed universes revealed an astonishing amount. They showed how dark matter halos merge, how galaxies fall into clusters, and how cosmic voids form between dense regions. They demonstrated the importance of gravitational collapse and helped confirm the cold, dark matter model as the dominant theory for cosmic structure formation. And perhaps most importantly, they gave scientists a playground to test ideas that couldn't be tested in the real world. After all, you can't rerun the actual universe. You can't tweak a parameter and see what happens. But in a simulation, you can. You can change the amount of dark matter, adjust the expansion rate, or add a new type of feedback process. Then you hit run and watch your synthetic universe unfold. The early days of cosmological simulation were marked by limitations, of course. The resolutions were low, the physics was simplified, and many of the results depended heavily on assumptions. But the foundation was laid. Scientists had learned that gravity could sculpt complexity out of simplicity, and that digital tools could reveal patterns too large, too slow, or too distant to observe directly. What started as a few dots on a primitive screen had become something far more powerful, a new way of seeing, not just the universe as it is, but the universe as it might have been, or might still become, and all of it, somehow, living quietly inside a box. In the early 2000s, a team of scientists decided to build something wildly ambitious, a digital universe so vast, so detailed, and so thoroughly rooted in modern physics that it would stretch the limits of what supercomputers could handle. This was not a movie plot or an academic exercise tucked away in a dusty folder. It was real, and it would go on to become one of the most influential simulations in the history of cosmology. Its name was the Millennium Simulation, and is aimed to capture the entire visible universe, not in perfect clarity, of course, but in astonishing detail for its time. Run in 2005 by the Max Planck Institute for Astrophysics in Germany, the Millennium Simulation modelled the evolution of cosmic structure from about 400,000 years after the Big Bang all the way to the present day. That's over 13 billion years of expansion, collapse, clumping, and reshaping. all compressed into a sprawling numerical ballet. To make it happen, scientists used 10 billion particles. Not real particles, of course, but computational ones. Each one stood in for a massive amount of dark matter, and together they mapped out a chunk of the universe 2 billion light-years across. Let's pause on that for a moment. 2 billion light-years. That's about 1/15 the size of the observable universe. Imagine simulating a cube of space so large that it includes tens of millions of galaxies, with all their motions governed by gravity alone. Then imagine trying to track how each of those galaxies forms, moves and clusters over the course of cosmic history. It was like attempting to simulate the weather for an entire planet. Not just for a week, but for billions of years, and yet the Millennium simulation did exactly that. But what made it special wasn't just its scale, it was the precision, the ambition, and the philosophical weirdness of what it represented. For the first time, scientists could study the cosmic web not just as a theoretical construct or a telescope image, but as a living, evolving structure. They could watch how dark matter halos emerged, merged, and grew. They could examine how galaxies formed within these halos and how those galaxies clustered into filaments, bridges, and walls across cosmic space. And they could do all of it inside a machine. To run a simulation of this magnitude, you need serious computational muscle. The Millennium simulation was executed on a supercomputer named the Garching Rechenzentrum, a high-performance cluster that, while modest by today's standards, was a monster in its day. It crunched through the equations of gravity for months, updating the position and velocity of every particle in the simulation again and again, as cosmic time ticked forward in small, calculated steps. The output of the simulation wasn't a pretty picture, not at first. It was raw data, petabytes of it, trillions of floating point numbers describing where each particle was at each point in time. But once this data was processed and visualized, it revealed something extraordinary. A digital version of the large-scale universe that looked hauntingly familiar. Filaments and clusters sprang into view. Cosmic voids stretched across the simulated sky. It was as if someone had taken a slice of reality and turned it inside out, rebuilding it from first principles and letting it unfold. Of course, the Millennium simulation didn't simulate everything. It focused solely on dark matter, which makes up the bulk of the universe's mass and dominates the formation of cosmic structure. Ordinary matter, gas, stars and galaxies, was not directly simulated. Instead, it was added later using semi-analytic models. These are mathematical recipes that take the dark matter framework and overlay a plausible story for how galaxies might form, evolve and die within it. It's a bit like baking a cake using only a skeleton of ingredients, and then decorating it afterward with frosting and sprinkles based on educated guesses. But even those guesses were grounded in real observations, from the Sloan Digital Sky Survey, the Hubble Space Telescope, and other astronomical missions. The result was a simulation that not only matched what we saw in the sky, but helped explain why we saw it. The importance of this simulation can hardly be overstated. It allowed scientists to run virtual surveys of the universe. They could pretend to be an astronomer inside the simulation, point their virtual telescope in a direction, and see what kinds of structures would appear. These mock observations could then be compared to real data, helping to identify inconsistencies, biases, and gaps in understanding. If a real telescope showed more galaxies in one region than the simulation predicted, it raised a flag. Was the simulation missing some physics, or was the telescope detecting something unexpected? It also helped settle debates. For example, there was ongoing tension between different cosmological models, particularly warm dark matter versus cold dark matter. Warm dark matter particles move faster, which can erase small-scale structure. Cold dark matter moves slowly and allows finer clumping. The Millennium simulation strongly favoured the cold dark matter model, showing that it naturally produced the kind of cosmic web we actually observe, and yet The word millennium wasn't just a fancy title, it reflected the scope of the project, spanning cosmic time, illuminating 1 billion years of evolution, and establishing a new kind of benchmark. After its release, other researchers began designing follow-up simulations using even more particles, more sophisticated physics, and better resolution. But the Millennium simulation remained the standard bearer for years. It also raised deeper questions. If we can simulate the large-scale universe with such accuracy, what does that say about our understanding of the cosmos? Does this suggest we've solved the big-picture structure? Not quite. The simulation worked because it made certain assumptions, most notably about the nature of dark matter and the initial conditions of the universe. Those inputs were based on the best data available at the time, but they're still approximations. In other words, the Millennium simulation was a beautiful, complex, and extraordinarily informed guess. A guess that happened to work remarkably well, but it was still fundamentally a guess. And then there's the question of scale. The Millennium simulation had incredible breadth, but relatively limited resolution. Each particle represented a huge chunk of dark matter, millions of times more massive than the Sun. That meant smaller structures, like individual galaxies or satellite systems, were effectively smoothed over. To study those, different simulations were needed, ones that traded volume for detail. But the Millennium simulation showed the path forward. It proved that digital universes could be both meaningful and manageable, even when scaled to the billions. It also invited something rare in theoretical physics: beauty. The visualizations produced from Millennium data were stunning. Vast webs of light tracing the invisible structure of space, like frost patterns on a cosmic windowpane. They didn't just inform, they inspired. Students, scientists, and stargazers alike could look at these images and feel, in some deep and quiet way, that they were seeing the bones of reality. At the time, some joked that the simulation was so detailed, we might as well live inside it. A tongue-in-cheek reference, but one that hints at something quietly profound. If a simulated universe can match our own in structure and behaviour, how do we define what's real? That's a philosophical question, and the simulation doesn't answer it. But it does make the question harder to ignore. Ultimately, the Millennium simulation was a turning point. It was the moment when simulations stopped being crude approximations and started becoming laboratories, places where theories could be tested, hypotheses refined, and the universe itself poked and prodded like a patient on a cosmic examining table. It reminded us that even with invisible forces and unknown particles, we can still model something astonishingly close to truth. And all of it began with a bold idea, 10 billion particles, and a box large enough to hold a piece of eternity. If the Millennium simulation was a grand sketch of the cosmos, a sweeping map of structure and form, then Illustrious was the beginning of digital astronomy's renaissance. Launched in 2014 by an international team of astrophysicists, the Illustrious simulation took the idea of building a universe and brought it into high definition. Not only did it track the dark matter scaffolding of the universe, but it also modelled how gas flows, stars ignite, black holes feed, and galaxies evolve. And it did all of this with a level of visual beauty that made even hardened scientists stop and stare. Where earlier simulations focused primarily on dark matter and used basic approximations to represent visible structures, Illustrious aimed to model both the invisible and the luminous. It sought to show not just where galaxies form, but how they grow, interact, merge, and scatter their starlight across billions of years. The result wasn't just more accurate, it was astonishingly lifelike. Spiral galaxies swirled with grace, massive ellipticals glowed with the fiery chaos of ancient collisions. Intergalactic gas streamed and pooled like water caught in cosmic tides. The numbers behind it were no less impressive. Illustrious simulated a cube of space about 350 million light-years across, using over 12 billion resolution elements, particles and fluid cells that represented gas, dark matter, stars, and black holes. Each of these elements carried its own properties. mass, velocity, temperature, chemical composition. As the simulation ran, these properties evolved in response to physics equations governing gravity, hydrodynamics, star formation, radiation, and more. At the heart of the simulation was a clever algorithm called a repo. Unlike traditional grid-based simulations which divide space into fixed boxes, a repo used a moving mesh, essentially a flexible grid that adapts to the flow of matter. This allowed Illustrious to maintain both high accuracy and computational efficiency, even in regions with complex dynamics, like star-forming galaxies or turbulent gas clouds. It was like watching a digital universe breathe, stretch and swirl as it expanded through time. But what really set Illustrious apart wasn't just the fidelity, it was the scope. The team ran multiple simulations at different resolutions, balancing size and detail. They included feedback processes from stars and supermassive black holes, which play a crucial role in shaping galaxies. When stars go supernova, they blast energy into their surroundings, stirring gas and slowing down further star formation. Black holes do something similar, but on a much grander scale, spewing jets of hot gas that can push material out of galaxies altogether. These feedback mechanisms are tricky to model. They occur on small scales, but their effects ripple across cosmic distances. In Illustrious, the team used calibrated subgrid models to capture this behaviour, allowing the simulation to generate realistic galaxy populations. And when they compared the simulated galaxies to real ones, from telescopic surveys and deep field images, they found remarkable similarities. The distribution of galaxy shapes, masses and colours all lined up surprisingly well. That said, Illustrious wasn't perfect. Some galaxies were too massive, others too compact. The simulation tended to overproduce stars in certain environments, a known challenge in many early models. But the point wasn't perfection, it was progress. Illustrious showed what was possible when you combine physics, computation, and just the right touch of artistry. And speaking of artistry, the visualizations from Illustrious were stunning. Using the raw simulation data, the team created images and animations that looked less like scientific plots and more like cosmic paintings. Wisps of gas glowed in false colour. Galaxies twirled and tumbled in kaleidoscopic dances. These visuals weren't just for show, they helped researchers understand how matter moved, how feedback spread, and how different processes shaped structure. But they also had an unexpected side effect. They inspired. People outside of the scientific community, including artists, educators, and even poets, found themselves drawn to this digital cosmos. Suddenly, cosmological simulations weren't just analytical tools, they were portals into a hidden universe, alive with motion and a mystery. Building on the success of Illustrious, the team launched an even more advanced project, Illustrous TNG, short for the next generation. This suite of simulations improved on nearly every aspect of the original. The largest run, known as TNG 300, covered a volume nearly 10 times larger than the original Illustrious, while still maintaining high resolution. It incorporated improved models for magnetic fields, stellar winds, galactic feedback, and chemical enrichment. It even tracked the production of heavy elements over cosmic time, allowing researchers to study how galaxies become enriched with carbon, oxygen, and iron, the very stuff that makes life and planets possible. Illustrous TNG was particularly good at capturing the diversity of galaxies. It produced realistic-looking spirals, lenticulars, irregulars, and massive elliptical systems. It also allowed scientists to study how galaxies evolve in different environments, isolated in voids, packed in clusters, or streaming along the filaments of the cosmic web. The simulation revealed how galaxies interact with their surroundings, exchanging gas, triggering starbursts, and sometimes quenching entirely, going silent after a brilliant youth. One of the more striking insights from TNG was the role of supermassive black holes. These aren't just exotic features at the centres of galaxies, they're active participants in galactic evolution. The energy released from accreting black holes can heat surrounding gas, shut down star formation, and even blow matter out into intergalactic space. In the simulation, this feedback was essential for reproducing the observed population of massive dormant galaxies we see today. And just like its predecessor, Illustrous TNG produced visuals that seemed to hover between science and dreamscape. Filaments of dark matter stretched like neural pathways. Galaxies blaze like fireflies in the dark. Gas clouds rippled with colour-coded temperature maps. In many ways it was a form of storytelling, just one told in the language of physics and code. But behind all the beauty was something deeply scientific. These simulations weren't guessing at reality. They were working hypotheses, grounded in observation and theory. Researchers could use them to test ideas, measure outcomes, and explore alternate versions of the universe. What happens if star formation is more efficient? What if black holes release more energy? What if dark matter behaves differently? With each tweak and rerun, the simulations became a kind of dialogue between theory and observation, between what we know and what we imagine might be true. These simulations also reminded us of how far we've come, from a few dozen particles bouncing around in early n-body simulations to tens of billions of resolution elements tracing the evolution of galaxies. The field has grown exponentially. But with that growth comes humility. As detailed as Illustrious and TNG are, they still rely on simplifications, they still make assumptions, and they still leave out phenomena we don't fully understand. Yet even with those caveats, the simulations tell a compelling story. They show us a universe that is not only governed by rules, but also full of surprises. A universe where complexity arises from simplicity, where structures form and fade in a cosmic dance that spans eons. And they do all of this with elegance, with a kind of precision that somehow feels poetic. In the end, Illustrious and its successors aren't just about simulating galaxies. They're about understanding where we fit into a much larger picture. They invite us to see the universe not just as observers, but as participants in a shared journey of discovery. And if that journey happens to look breathtaking while it unfolds, well, all the better. At first glance, a galaxy simulation doesn't look like much, just a long string of numbers, coordinates, velocities, masses, temperatures. A soup of data points whizzing around a virtual space, but inside those numbers, hidden beneath all the decimals and floating point values, something beautiful is quietly taking shape. Given the right tools and enough time, those numbers become a galaxy, spiraling, glowing, alive in the way only science and imagination can make possible. The transformation from data to galaxy begins with motion. Every particle in a simulation, whether it's standing in for dark matter, gas, or a star, has its own position and velocity. These aren't static dots on a canvas. They're evolving according to the laws of physics. At every time step, perhaps every million years of cosmic time, the simulation calculates how each particle moves in response to forces like gravity, pressure, and radiation. It's a silent choreography, and it happens one frame at a time. Gravity is usually the first sculptor on the scene. Even in the earliest stages of a simulation, long before stars or galaxies appear, gravity begins drawing matter together. Over millions of years, tiny fluctuations in density start to grow. Small clumps become larger clumps. Larger clumps pull in even more mass. This process, called gravitational instability, is what gives rise to halos of dark matter, the invisible skeletons around which galaxies will eventually form. Dark matter doesn't glow, but it provides the scaffolding. Without it, the luminous parts of the universe would drift apart like fog without form. Once a dark matter halo becomes dense enough, it begins attracting ordinary matter, gas made of hydrogen and helium left over from the Big Bang. As gas falls into the halo, it heats up, compresses, and starts to swirl. This is where things start to get interesting. In the simulation, gas is usually modelled using fluid dynamics. That means tracking not just where it goes, but how it moves, how it compresses, cools, shocks, and flows. Simulations often use smooth particle hydrodynamics or grid-based solvers to model these behaviours. Either way, the gas isn't just moving through space like a gentle breeze, it's alive with turbulence, eddies, and compression waves. Some regions grow dense and cold enough to trigger star formation. But wait, how does a simulation know when a star is born? This is where things become part physics, part clever programming. Real star formation is a chaotic and complex process, involving molecular clouds, magnetic fields, and a whole lot of messy astrophysics. No simulation can capture all of that directly, so instead they use a recipe, a star formation algorithm. When a region of gas in the simulation hits certain conditions, usually high density, low temperature, and enough mass, it is flagged for star formation. The simulation then converts some of that gas into star particles. Now, a star particle isn't a single star. It's usually shorthand for a collection of stars, often millions or even hundreds of millions packed into one data point. Each star particle carries properties like age, mass, and metallicity, the amount of heavy elements it contains. Over time, the simulation tracks how these star particles evolve. Some grow older and fade, some explode as supernova, blasting energy and material back into the surrounding gas. This feedback process stirs the pot, influencing future star formation and shaping the structure of the galaxy. It's at this point that pixels begin to shine. The raw simulation is still just numbers, but once we visualize it, translating mass into brightness, temperature into color, and density into contrast, we start to see the form emerge. Spiral arms twist out from glowing centers. Elliptical galaxies puff out like cosmic clouds. Streams of gas arc between galaxies like quiet fireworks. And all of this comes not from artistry, but from physics. The simulation didn't draw the spiral. It simply followed the math of angular momentum and gravitational collapse, and the spiral appeared. These visuals aren't just pretty pictures, they carry meaning. Scientists use them to analyze the distribution of stars, the behavior of gas flows, and the impacts of various feedback mechanisms. By comparing simulated galaxies to real ones, those observed by telescopes like Hubble or James Webb, researchers can test whether their models are accurate. Do the simulated galaxies have the right colors? Do they rotate at the correct speeds? Do they contain the right mix of old and young stars? If the answers are yes, that's a sign the simulation is on the right track. If not, it's back to the code to tweak the recipe. One of the striking things about these visualizations is just how intuitive they can be. You don't need to be an astrophysicist to recognize a spiral galaxy, or to notice when something looks off. Our brains are wired to pick up patterns, especially natural ones. And galaxies, despite their vastness and complexity, often follow familiar forms. Seeing them emerge from pure simulation feels like watching a flower bloom in slow motion, unexpected and yet perfectly logical. Sometimes, the most astonishing part is what wasn't planned. Simulations can produce structures that surprise even the researchers running them. A stream of stars torn from a disrupted satellite galaxy. A filament of gas twisted into an elegant arc. A void so vast and clean it seems to echo. These are not designed features. They emerge naturally from the code, the physics, and the way matter evolves over time. This emergence is what gives simulations their unique power. They don't just reflect what we already know, they generate possibilities. They allow us to witness the kinds of structures that could exist, given the right conditions. Some of those structures match what we see in the real universe, others don't. But even the mismatches are valuable. They tell us where our understanding falls short, where the models need improvement, or where new physics might be hiding. Of course, to turn simulation data into something viewable, you need more than just code. You need visualization software. Tools like YT, OpenSpace, and various custom rendering engines allow scientists to translate numbers into images. These programs apply color maps, simulate lighting, and allow zooming through layers of structure. Some even generate cinematic fly-throughs of the simulated universe, letting you coast past virtual galaxies like a slow-motion comet. The end result is something both analytical and artistic, a bridge between raw computation and human perception. And because simulations can run over cosmic timescales, we can watch a galaxy form in mere seconds, collapsing, rotating, lighting up with stars, and interacting with its neighbours. In the real universe, this would take billions of years. But in the simulated one, it's just a matter of frames. Even though simulations are carefully tuned to reflect what we observe, they can also point to what we haven't yet seen. A simulated galaxy might suggest a certain kind of merger we've never observed, or a gas halo that could be detectable with future telescopes. In this way, simulations don't just recreate reality, they extend it. They provide a glimpse into the unseen, the unmeasured, and the not yet known. At their core, these pixelated galaxies remind us of something simple but profound, that the universe operates by rules, and when we understand those rules, even just a little, we can start to build pieces of it ourselves, not with atoms but with algorithms, not with telescopes but with time loops and lines of code. And out of that digital ether, galaxies appear. They shimmer, they spin, they interact and evolve. And for a moment it almost feels like we're watching something real, not because we faked it well, but because we understood just enough to let the rules take over. In that sense, the pixels aren't pretending to be galaxies. They are galaxies, just in a different form. Galaxies born of gravity, fluid dynamics, and computational patience. Galaxies that speak the language of the cosmos, one line of data at a time. Imagine trying to paint a landscape when the most important feature in it is completely invisible. The trees sway, the rivers twist, and the hills cast shadows, but there's something massive, quiet, and entirely unseen holding it all together. That's what it's like trying to simulate dark matter. You can't see it, you can't touch it, and no telescope will ever take a picture of it. Yet, in cosmology, dark matter is the silent architect. It shapes galaxies, carves out cosmic filaments, and keeps the universe from flying apart at the seams. So how do scientists simulate something so elusive? The first step is admitting we don't fully know what dark matter is. We know it's not made of ordinary atoms. It doesn't emit light, absorb it, or reflect it. It doesn't form stars or planets, and it doesn't interact with electromagnetism at all. It does, however, interact with gravity, and that's where simulations get their grip. From the very first galaxy rotation curves measured in the 20th century, astronomers knew something was off. Galaxies were spinning too fast for their visible matter to hold them together. It was like watching a carousel whirl around with no one visibly riding it, and yet somehow the horses stayed firmly on their poles. The only explanation that made sense was that galaxies contain much more mass than we can see. This extra mass, dark matter, exerts gravitational force even though it remains unseen. In a simulation, gravity is the universal equalizer. If you have mass, you affect the motion of everything around you. That means scientists can include dark matter in their models by assigning it mass and letting it interact gravitationally with everything else. Even though we don't know its exact nature, we can make educated guesses about its behaviour based on what the universe looks like today. To start, cosmologists use data from the early universe, particularly the cosmic microwave background, to set the initial conditions. This data gives us a map of tiny fluctuations in the density of matter just a few 100,000 years after the Big Bang. Then, they distribute dark matter particles across the simulation according to those fluctuations and let gravity do the rest. The particles themselves don't represent individual bits of dark matter. Instead, each one stands in for a large clump, sometimes the equivalent of several million suns worth of invisible mass. These particles don't clump like gas or condense into stars. They don't cool down or radiate heat. They simply float, drift, and cluster, driven only by their mutual gravitational attraction. Over billions of years, these particles begin to collapse into dense halos. These halos grow by merging with others and attracting more matter. They don't shine, but their effects are unmistakable. Inside these halos, galaxies can form. Outside them, the universe remains sparsely populated. In this way, dark matter creates the cosmic scaffolding, the hidden skeleton on which all visible structures are built. Simulations show that dark matter naturally arranges itself into a vast interconnected web. Filaments stretch across space like strands of a spider's silk, intersecting at nodes where halos grow large and complex. These nodes become the homes of galaxy clusters. The voids between them remain relatively empty. This structure, known as the cosmic web, appears in both simulations and observations, giving us confidence that our invisible guesswork is eerily accurate. What's even more striking is that simulations using only dark matter, no gas, no stars, no black holes, can still reproduce the large-scale structure of the universe. That's how dominant it is. Even without light, dark matter can sketch the outline of everything we see. Of course, no simulation is complete with just dark matter. To understand galaxy formation, you need to include ordinary matter too, gas that can cool and form stars. But adding gas is complicated. It interacts in ways dark matter doesn't. It compresses, heats up, collapses and radiates. And that's where the two components begin to diverge. In the early universe, dark matter and gas were more or less in sync, but as time progressed, their paths began to split. Gas started forming galaxies, stars, and feedback loops. Dark matter, indifferent to all that noise, continued drifting, collapsing quietly, like an orchestra conductor that never once plays a note but sets the pace for everything else. One challenge in simulating dark matter is deciding how much detail to include. Since we can't observe it directly, we rely on theory. The most popular model is cold dark matter, where cold means that the particles move slowly compared to the speed of light. This allows them to clump more easily and form small structures. But there are competing ideas. Warm dark matter, for instance, suggests slightly faster moving particles that smooth out the small-scale clumps. These differences show up in simulations. Cold dark matter produces a universe full of fine detail, tiny galaxies, satellite systems and thin filaments. Warm dark matter smooths out the landscape, producing fewer small structures. By comparing simulations with telescope surveys, astronomers can test these models. If a simulation predicts thousands of dwarf galaxies orbiting the Milky Way, but we only observe a few dozen, something might be off. This has led to ongoing debates about whether we've truly nailed down the nature of dark matter, or whether we've just found a good enough approximation. Another fascinating feature of dark matter simulations is how they reveal halo structure. Simulations show that dark matter halos have dense centers and gradually thinning outer regions. These halos are not solid spheres, but more like fuzzy cocoons, shaped by countless mergers and interactions. The more massive the halo, the more likely it is to host a large galaxy, or a cluster of galaxies. And at the centre of nearly every large halo sits a supermassive black hole, another mysterious object that seems to thrive in the dark. But the real magic happens when you combine dark matter simulations with models of galaxy formation. The result is a universe that doesn't just match our observations, it helps explain them. It shows how galaxies can form where they do, how clusters emerge, and why the universe looks the way it does on both large and small scales. Despite all of this, dark matter remains a mystery. We've never caught a particle in a lab. We don't know what it's made of, whether it's a WIMP, an axion, or something else entirely. Yet in simulations it behaves with remarkable consistency. It holds galaxies together, shapes the web of matter, and plays by the gravitational rules we know so well. In some ways, simulating dark matter is like listening for a silent instrument in an orchestra. You can't hear it directly, but its influence is everywhere. The melody feels wrong when it's missing, the rhythm breaks, but when it's there, even invisibly, everything holds together. Perhaps that's the strangest part of all, that the thing we understand the least might be the one thing that holds the universe together the most. Simulations remind us that sometimes belief in the unseen isn't guesswork. It's pattern recognition. It's the ability to trace the footprints of something too quiet to speak, too elusive to capture, and too important to ignore. And even though we may never see dark matter with our eyes, we see it in every spiral galaxy, every gravitational lens, every cluster drifting in the void. We see it in the way the universe breathes, and in our simulations, it comes alive, not with light, but with gravity, guiding the visible world from the shadows. Every simulation begins with a choice about what to include, and just as importantly, what to leave out. Because no matter how powerful your computer is, or how clever your code may be, you can't model everything, not all at once, not in perfect detail. That's not a flaw, it's a feature of how science works. A simulation is not a mirror, it's a map. And like all maps, it simplifies reality to make it understandable. Cosmological simulations are no different. They aim to capture the broad strokes of how the universe evolves, the rise of galaxies, the growth of structure, the movement of dark matter and gas across time and space. But to do that, they must make assumptions, shortcuts, approximations. Sometimes those choices are harmless, even helpful. Other times, they subtly nudge the simulation off course. Let's start with resolution. Just like a photograph has pixels, a simulation has resolution elements, particles, cells, or points in a grid. The more of these you have, the more detail you can capture. But there's always a limit. You can't simulate every atom, not even every star. So simulations bundle things together. A single star particle might represent an entire cluster of stars. A gas cell might span light years. This approach smooths over the fine-grained chaos of real physics, replacing it with an average, a best guess. This means that small-scale processes, like individual supernova explosions or the turbulent swirl of interstellar gas, are not directly modelled. They're parameterized instead. That is, their effects are folded into the simulation through simplified recipes known as subgrid models. These are equations that say, when this happens, we'll pretend that this other thing follows, even if the actual physics is more complicated. Take star formation, for example. In reality, it depends on molecular chemistry, magnetic fields, dust dynamics, and more. In simulations, it's often triggered when gas hits a certain density and temperature threshold. That threshold is chosen by researchers and tuned to match observed galaxies. It's a practical solution, but not always a perfect one. If the parameters are too generous, galaxies form too many stars. If they're too strict, galaxies become barren. Then there's feedback. How stars and black holes return energy to their surroundings. In the real universe, exploding stars blast gas outward in chaotic waves. Active galactic nuclei can drive powerful jets, heating and stirring gas across thousands of light years. In simulations, these effects are modelled by injecting energy into gas cells, often in a controlled and uniform way. But nature is rarely uniform. Sometimes the simulated blast is too weak to do much. Other times, it sweeps entire galaxies clean, shutting down star formation too quickly. Calibrating this feedback is one of the trickiest parts of simulation design. And what about the magnetic fields? These invisible threads run through space, guiding charged particles, shaping gas flows, and possibly influencing galaxy formation in ways we don't yet fully understand. Some advanced simulations include magnetohydrodynamics, fancy physics that combines fluid motion and magnetic fields, but many still leave it out, or simplify it to avoid the heavy computational cost. Cosmic rays are another missing ingredient in many models. These high-energy particles can travel across galactic scales, transferring momentum and heating gas in subtle but important ways. Including them adds complexity, so most simulations assume they're negligible. But new studies suggest they might play a larger role than we once thought, especially in regulating star formation and galactic winds. Even the laws of gravity, so central to cosmic evolution, are sometimes simplified. Most simulations use Newtonian gravity, which works well in most cases. But general relativity tells us that gravity is actually a curvature of space-time, and in extreme environments, like near black holes or during the early universe, those relativistic effects could matter. Including them accurately requires a lot more math and processing power. So many simulations assume Newton's laws are close enough. And then there's chemistry. Real gas clouds aren't made of pure hydrogen and helium. They contain metals, astronomy's catch-all term for every element heavier than helium, produced in stars and spread by supernovae. These metals influence how gas cools, how stars form, and even how light travels through space. Many simulations include simplified models of chemical enrichment, but tracking dozens of elements across billions of years is computationally expensive. As a result, some simulations use a single metallicity value to represent all heavy elements, glossing over the rich detail of galactic chemistry. Radiation, too, is often handled in a rough and ready way. Light affects matter. It heats gas, ionizes atoms, and pushes dust around. But modelling how radiation travels and interacts with everything else is incredibly complex. Some simulations use basic radiative transfer models, but many opt for approximations, assuming uniform backgrounds or simplified light sources. This can work well on large scales, but it can miss critical local effects, like how a nearby star cluster might carve out a bubble in a dense gas cloud. Of course, one of the biggest unknowns is dark matter. While simulations can model its gravitational effects beautifully, they don't simulate the particles themselves. That's because we don't know what they are. We assume they're cold, collisionless, and non-interacting, because that's what matches observations. But if dark matter has even slight interactions, or if it turns out to be something exotic like fuzzy dark matter or a whole spectrum of particles, our current models may be subtly off target. The same goes for dark energy. Most simulations assume a simple cosmological constant, a uniform energy density that causes the universe to expand faster over time. But what if dark energy evolves? What if it interacts with other fields or changes its behaviour over cosmic history? Those scenarios are harder to simulate and often get left out in favour of simpler models. All of these exclusions and approximations add up. And while simulations are remarkably successful in reproducing many features of the universe, their blind spots can lead us astray. Sometimes a mismatch between simulation and observation isn't a sign that nature is surprising, it's a sign that something was left out, a missing ingredient, an oversimplified recipe, and yet these gaps don't render simulations useless. Far from it. In fact, they highlight one of their greatest strengths, the ability to test our assumptions. By comparing different models, changing one ingredient at a time, researchers can explore how sensitive cosmic structures are to the physics involved. If including magnetic fields changes the outcome, that tells us something. If cosmic rays flatten the central density of a galaxy, that's a clue. Simulations become laboratories for physics we can't test any other way. The key is to treat simulations not as predictions, but as hypotheses. They're guesses dressed in code, refined over time through trial and error. And every gap, every shortcut, is a potential opportunity to learn something new, to ask a different question, to build a better model. In some ways, the gaps are what make simulations so human. They reflect our limitations, our incomplete knowledge, our computational constraints, our need to simplify in order to understand. But they also reflect our creativity, the ability to take a messy, complicated universe and distill it into something we can explore, adjust, and test. So the next time you see a gorgeous image of a simulated galaxy, remember, you're not just looking at a model of what we know, you're also looking at a monument to what we don't. And in those empty spaces, those quiet, unresolved gaps, is where the real frontier begins. Picture a jigsaw puzzle of the universe, a really big one. Maybe 1 trillion pieces spread across cosmic time, from the afterglow of the Big Bang to the swirl of a spiral galaxy drifting in the present day. Now imagine trying to piece it together, not with your fingers, but with math, memory, and a supercomputer the size of a room. You could zoom in to admire the delicate shape of a star-forming cloud, or zoom out to see how galaxy clusters thread across space like luminous beads on invisible string. But here's the problem. You can't do both at once. This, in essence, is the challenge of resolution in cosmological simulations. In the digital cosmos, resolution refers to the smallest detail you can model. It's how finely your simulation slices time, space, and matter. The higher the resolution, the more precisely you can trace the motion of gas, stars, and dark matter. But like any high-resolution image, it comes at a price. More detail means more data, more particles, more computations, and eventually more time than any computer has to spare. Imagine trying to simulate an entire universe with the same level of detail you'd use to model the atmosphere of a single planet. You'd need a particle to represent every molecule of hydrogen, a time step small enough to capture every flicker of plasma, and memory to hold trillions upon trillions of calculations. You'd need a machine the size of a galaxy, and patience that spans eons. So scientists make a choice. They compromise. And understanding those compromises is key to understanding what simulations can and cannot do. Let's start with spatial resolution. In a cosmological simulation, the universe is divided into a grid or filled with particles. Each grid cell or particle represents a chunk of matter, sometimes as small as a few light years across, sometimes as large as a galaxy itself. This is the basic pixel of the simulation. If you want to resolve smaller structures, you need smaller pixels. But reducing the size means increasing the number, and that increases the computational load exponentially. A simulation like Illustrous TNG, for instance, might use tens of billions of resolution elements to model a volume of space several 100 million light-years across. That's impressive, but it still means that individual galaxies are made of just a few thousand star particles and gas cells. A single spiral galaxy in the real universe has hundreds of billions of stars. The simulation sees it as a soft digital smear. That's not a bug, it's a feature of the scale being modelled. These simulations are designed to study the statistical properties of galaxies, not their individual quirks. They're trying to answer big questions. How do galaxies cluster? What role does dark matter play? How does feedback regulate star formation across billions of years? To answer these questions, you don't need to model every solar system. You just need to capture the overall behaviour of matter on large scales. But suppose you want to simulate a single galaxy in exquisite detail. In that case, you'd zoom in, shrink your simulation volume, and increase your resolution. This lets you model the dynamics of gas clouds, star-forming regions, and black hole jets with much greater precision. But it also means you lose the big picture. You can't model an entire universe and a molecular cloud at the same time, not without cutting some serious corners. This trade-off is sometimes called the resolution problem, but it's more of a balancing act. If you go too low in resolution, you miss critical processes. You might smooth over small galaxies, wash out star clusters, or fail to capture feedback from supernovae. If you go too high, your simulation grinds to a halt before it finishes. It's like trying to draw the Mona Lisa using only a microscope. You'll nail the eyelashes, but you'll forget the smile. Then there's temporal resolution, the size of the time steps in your simulation. The universe changes slowly, but not always. Collapsing gas clouds, exploding stars and galaxy mergers can happen rapidly, at least by cosmic standards. If your simulation skips too many steps, you might miss these moments entirely. But smaller steps mean more iterations, and more iterations mean more computing power. Simulations often use adaptive time-stepping to balance this. Regions that evolve quickly, like the heart of a star-bursting galaxy, get updated more frequently. Quieter regions, like the voids between clusters, can coast along on slower clocks. This allows the simulation to focus its resources where they're needed most, without wasting time on empty space. But even with clever techniques, limitations remain. Feedback processes, in particular, are sensitive to resolution. A supernova in a low-resolution simulation might simply heat up a large gas cell and disperse quietly. In a high-resolution version, the same event could drive complex shockwaves, trigger new star formation, or even blow apart part of a galaxy. What looks like a harmless puff in one model might be a dramatic outburst in another. That's why many simulations include convergence tests, running the same model at different resolutions to see how stable the results are. If the galaxy still looks roughly the same, regardless of pixel size, that's a good sign. If it changes dramatically, the simulation might be too sensitive to its own limitations. Resolution also affects how accurately you can track the formation and evolution of small galaxies. In low-resolution simulations, these tiny systems often get washed out entirely. This has consequences for studying the faint end of the galaxy population. The dwarfs, satellites, and ghostly structures that may carry important clues about dark matter and cosmic history. There are creative ways around these problems. One is the zoom-in technique. Scientists run a low-resolution simulation of a large cosmic volume, then identify a region of interest, say, a particular galaxy or cluster, and resimulate just that region at much higher resolution. This lets them study detailed physics in a realistic cosmic context. It's like watching a city develop within a continent-wide map. You get the local details without losing the global setting, but zoom-ins come with their own trade-offs. They require complex data handling and careful setup to make sure the transition between scales is smooth, and they can't easily be generalized to study large populations. If you want to simulate thousands of galaxies at once, zoom-ins are too slow and too focused. Another approach is to combine simulations with machine learning. By training algorithms on high-resolution data, researchers can teach them to fill in small-scale details in lower-resolution models. It's not perfect, but it's promising, an attempt to stretch the limits of resolution without increasing the cost. At the heart of all this is a basic truth. You can't have it all. Every simulation is a compromise between scope and precision, between modelling everything and modelling anything well. Scientists have to choose where to focus, which features to prioritise and which imperfections they're willing to accept. And yet, despite these compromises, the results are nothing short of extraordinary. Even with their blurry pixels and smoothed-over galaxies, simulations have helped us understand how the universe evolved from a sea of hot gas into the richly structured cosmos we see today. They've shown us how dark matter sculpts space, how galaxies collide and grow, and how feedback from stars and black holes shapes the fate of everything around them. It's easy to think of resolution as a technical detail, a constraint imposed by hardware, but it's also a philosophical choice. It reflects our priorities, our questions, and our curiosity. Do we want to understand the broad patterns of the universe, or the intimate details of one galaxy's life? Either path offers insight. Both paths require trade-offs. In the end, cosmic resolution isn't about seeing everything. It's about seeing enough. Enough to make sense of the noise, enough to ask better questions, enough to glimpse the structure beneath the chaos, and sometimes, even through the blur, the universe still manages to take your breath away. Running a cosmological simulation can feel a bit like baking a cake without a recipe. You know some of the ingredients, gravity, dark matter, gas, but others are uncertain. Maybe you're not sure how much feedback to add, or when star formation should begin, or how violently a black hole ought to burp after lunch. You mix, you bake, you check the results. If the galaxy comes out too puffy or the cosmic void's too shallow, you tweak the mix and try again. It's science, absolutely. But it's also something closer to guided art. This is where calibration comes in. In principle, a perfect simulation would use only well-established physics, No adjustments, no tuning, no fudging. It would predict the universe exactly as we see it, right out of the box. But real-world simulations aren't quite that pure. The cosmos is complex, and our understanding of it is incomplete. That means simulations often include parameters that don't come straight from nature. They come from us, from observation, estimation, and informed trial and error. Think of these parameters like knobs on a cosmic soundboard. Each one controls a different aspect of the simulation: how easily stars form, how energetic supernovae are, how gas cools, how black holes inject energy into their surroundings. These aren't arbitrary dials, but they also aren't fixed by theory alone. They need to be adjusted, calibrated, until the output of the simulation resembles the universe we observe. This calibration process is often misunderstood. It's not about faking results or reverse engineering the outcome. It's more like setting the tempo before an orchestra begins. You know the symphony is written in a particular key, and you have a good idea how it should sound, but someone still needs to give the first downbeat. Calibration provides that rhythm. Let's take star formation efficiency as an example. In the real universe, not all gas turns into stars. In fact, most of it doesn't. Stars form only in specific conditions, often within cold, dense clouds, shielded from disruptive forces. But modelling those exact conditions in a simulation is nearly impossible. They happen on scales far smaller than most cosmological models can resolve. So instead, simulations include a parameter. Given a certain gas density and temperature, how likely is it that stars will form? If this parameter is set too high, the simulated galaxy becomes a star factory, spewing out bright blue giants at a rate that would make real astronomers raise their eyebrows. If it's set too low, galaxies struggle to shine. The key is to find a sweet spot, usually by comparing the simulation's galaxy population to those observed in the real sky. If the simulated galaxies have the same average brightness, structure, and star formation rate as observed ones, the calibration is working. But it doesn't stop there. Supernova feedback needs tuning too. When stars explode, they release enormous amounts of energy into their surroundings, heating gas and often pushing it out of galaxies entirely. This affects future star formation and can change a galaxy's shape and size. In simulations, this feedback is usually handled with a subgrid model, some form of energy injection into the surrounding gas. The exact strength and timing of that injection must be set by hand. Set it too low, and the galaxy becomes bloated with stars. Set it too high, and the galaxy expels all its gas and goes dark. Somewhere in the middle, the simulation matches reality. Disk galaxies form, star formation settles into a steady rhythm, and galactic winds puff out gently rather than exploding like popcorn. Now, let's turn to black hole feedback. In recent years, simulations have shown that the energy released by growing supermassive black holes plays a crucial role in shaping galaxies, especially the massive ones. Without this feedback, simulations tend to produce enormous elliptical galaxies bursting with new stars. Too many, too fast. But if black holes can heat or expel surrounding gas, they can slow or shut down star formation entirely. The challenge is figuring out how much feedback is appropriate. How often do black holes feed? How much energy do they inject into their environment? And how far does that energy spread? These aren't just theoretical questions, they're calibration points. If the simulated universe has too many giant galaxies with blue stars, scientists turn the knob a little. If it has too few luminous galaxies, they dial it the other way. It's not guesswork. It's guided iteration. Scientists run a simulation, compare the result to observational data, adjust the parameters, and run it again. Over time, the simulation converges on something remarkably close to the universe we observe. Galaxy luminosities match. Star formation histories line up. Gas fractions behave. It starts to feel like the model has captured something real. But of course, the danger is that if you calibrate too much, you risk building a universe that simply reflects your input biases. This is where the art becomes delicate. A well-calibrated simulation should reproduce multiple, independent observational properties without being tuned to each one directly. For example, you might calibrate your simulation to match the galaxy stellar mass function. How many galaxies exist at different masses, but then test it against something unrelated, like the gas distribution in galaxy clusters or the rate of star formation over time. If the simulation gets these other things right without additional tuning, it's a good sign that the underlying physics is realistic. It means the model isn't just a patchwork of fixes, it's a coherent system. Still, there's a playful tension here. Some scientists call the calibration process cosmic cheating, a tongue-in-cheek reference to how much fine-tuning is sometimes required. You're not falsifying data, of course, but you are nudging your simulated universe towards something that looks more familiar. And it raises a fair philosophical question. Are we discovering truths about the cosmos, or just engineering a reflection of what we already expect? The answer, perhaps, is a bit of both. Calibration is essential because we don't have all the answers. We don't know exactly how stars form or how black holes evolve. We can't simulate every magnetic ripple or photon. But we can build models that are consistent with what we see and use those models to learn more. Sometimes the best way to understand the universe is to try to build it ourselves, piece by imperfect piece. And when a simulation, calibrated just right, produces a galaxy that rotates at the right speed, shines with the right light, and contains the right mix of stars and gas, there's something quietly beautiful about it. Not because it proves we're right, but because it shows we're close. That somewhere in the math and the models we've touched something real. It's like tuning a musical instrument. You're not inventing the notes, you're aligning with a deeper harmony. And when the chords finally resonate, the universe sings back. Maybe not perfectly, maybe not completely, but clearly enough to remind us that we're listening to something worth understanding. If you build a model of the universe and it looks remarkably like the one we see through our telescopes, filaments stretching across the void, galaxies clustering, stars flickering to life in swirling spirals, have you just confirmed your genius? Or have you staged a very well-rehearsed play? It's a question that quietly hums beneath every simulation. Are we predicting the cosmos, or are we just replaying it in high definition? On the surface, simulations look like the ultimate predictive tool. Feed in the laws of physics, sprinkle in some initial conditions, and let the code do its work. Wait a few thousand computational hours, and out pops a digital universe. If it matches what we see, we call it a success. But does that mean we've predicted the universe? Not quite. At least not in the way we usually think about prediction. The word predict carries a lot of weight. In weather forecasting, it means telling you whether you'll need an umbrella tomorrow. In finance, it means guessing the direction of the market. In cosmology, though, prediction is a murkier business. We're not trying to forecast where the Andromeda galaxy will be next Tuesday. We're trying to understand the big picture, how galaxies form, how structure evolves, and whether the universe we simulate bears a meaningful resemblance to the one we live in. But even that distinction gets tricky. When a simulation matches observational data, like the number of galaxies at a given mass, or the size distribution of voids, it feels like a win. And it is. But here's the twist. Most simulations are built using those very observations. They're calibrated, nudged, and tuned using real-world measurements. That means they're not purely predictive. They're often built, at least in part, to reproduce the universe we already know. This isn't cheating, it's more like rehearsal. A way of confirming that the laws and assumptions baked into the model can produce something realistic. But once you've rehearsed the play and nailed the performance, the real question is, can the simulation step off stage? Can it surprise us? Can it tell us something new? Something we haven't seen yet? Sometimes, yes. One of the most powerful ways simulations make meaningful predictions is by extending our vision beyond what's currently observable. For example, before the first large-scale galaxy surveys mapped the cosmic web in detail, simulations already show that dark matter should form a vast filamentary network, with galaxies clustering along the strands. When telescopes finally revealed that same pattern in the real sky, it was a vindication. The simulations had offered a preview, one grounded in theory, not in direct observation. Another area where simulations have real predictive power is in exploring the consequences of different physical models. Suppose you want to know what the universe would look like if dark matter were warm instead of cold, or what might happen if dark energy changes over time. You can't test those ideas with observations alone, not yet, but you can simulate them. Run the model. Let the universe evolve. See what patterns emerge. If the results don't match reality, the idea might be wrong. If they do, you've just outlined a possibility worth investigating further. Simulations can also reveal indirect consequences of known physics. For instance, the way feedback from supermassive black holes affects not just their host galaxies, but the surrounding intergalactic medium, or how minor tweaks in the initial density fluctuations of the early universe can alter the eventual structure of galaxy clusters. These aren't predictions in the fortune-telling sense, but they're forecasts of consequence. They show how physical laws, when set in motion, shape cosmic outcomes. Still, we must be careful. Just because a simulation matches something we observe doesn't mean it predicted it. Correlation is not causation, and convergence is not confirmation. It's entirely possible to tune a simulation to match known data and still miss the deeper truth. You might have the right answer for the wrong reasons. Imagine simulating a forest. If you match the number of trees, the average height, and the shape of the canopy, your model might look pretty convincing. But if your code thinks the trees are made of ice instead of wood, you've got a problem. The forest may look right, but the underlying physics is all wrong. In cosmology, that kind of error is harder to spot. You can't knock on a galaxy to check if it's hollow. That's why scientists treat simulations not as crystal balls, but as hypothesis generators. A good simulation doesn't just mimic the universe, it probes it. It lets us run controlled experiments, change variables, isolate effects. What happens if you turn off black hole feedback? What if you double the rate of star formation? These what-if scenarios help researchers understand which physical ingredients matter most, and which assumptions are truly essential. And yes, sometimes simulations do make bold, testable predictions. One famous example came from models predicting the existence of massive galaxy clusters at high redshift, long before they were actually observed. When telescopes eventually found them, it was a quiet confirmation that our understanding of structure formation was on the right track. Not perfect, but close enough to build confidence. Another example lies in gravitational lensing, the way massive structures bend light as it passes by. Simulations predicted how dark matter halos should distort the images of distant galaxies. When these distortions were later measured with remarkable precision, the models were vindicated. But perhaps the most humbling thing about simulations is how often they fail. A model that predicts too many small galaxies, a feedback mechanism that overheats the gas, a star formation rate that falls flat. These aren't just bugs, they're signals. They tell us something is missing, misunderstood, or oversimplified. And that's a form of prediction too, a prediction that something needs fixing. There's also a philosophical side to this. The universe, in all its complexity, doesn't have to match our expectations. It's under no obligation to be intuitive, elegant, or computationally convenient. So when a simulation does match reality, even approximately, it's astonishing. It suggests that the underlying laws are not only knowable, but that our limited brains, aided by machines made of metal and a math, can trace those laws to their logical consequences. So, do simulations predict? Yes. But not always in the ways we might hope. They don't forecast tomorrow's galactic weather. They don't tell us who wins in a duel between two merging clusters. What they do is offer a space for thought experiments made tangible. A way to explore the implications of theory in a dynamic, visual and testable form. And sometimes, just sometimes, they look forward in time. They point to future observations that will confirm or challenge their claims, They inspire new missions, new telescopes, new questions, and when those observations come in, we don't just get data, we get dialogue, a conversation between what we expected and what the cosmos decided to show us. In that sense, simulations are rehearsal, yes, but not just for science. They're rehearsal for understanding, for discovering where we've been too confident or too cautious, for training our intuition to align more closely with the deep rhythms of space and time. So whether they're predicting or just playing pretend, simulations remain among our most valuable tools for asking, what could the universe be doing, and why? And sometimes, in asking, we end up knowing. At first glance, a simulation might seem like a cosmic blueprint, structured, deterministic, and inevitable. You feed in the laws of physics, press the big red Start button, and watch the universe unfold as though it had no choice in the matter. But dig a little deeper, and you'll find something quietly rebellious humming beneath the equations. Randomness. It's not a flaw. It's not a glitch. It's a fundamental part of the machinery. In fact, without randomness, simulations wouldn't just be less interesting, they'd be less accurate. The universe, as we observe it, isn't entirely predictable. It has trends and laws, yes, but it also has wiggles. The fine structure of reality is shaped not just by rules, but by chances. Quantum mechanics alone guarantees that down at the tinier scales, the universe is governed by probabilities. A particle doesn't decide to be here or there. It exists in a cloud of possibilities until something forces it to make a choice. And even at grander scales, chance events accumulate. The merger of galaxies, the birth of stars, the tumbling path of a comet, each shaped by a mix of order and chaos. So when scientists build simulations, they don't just encode the rules, they include the randomness too. One of the first places probability shows up is in the initial conditions. Cosmological simulations often begin just after the Big Bang, using data from the cosmic microwave background. These ancient photons tell us that the early universe wasn't perfectly smooth. There were tiny fluctuations in density, little ripples in the primordial soup. But we don't know exactly what those ripples looked like in every region of space. We only know the statistical properties, how big the ripples tended to be, how often they occurred, and how they were distributed. So simulations generate these fluctuations randomly, following the statistical pattern we've observed. Each run starts with a unique arrangement, slightly different bumps and dips, seeded using random numbers. These fluctuations act as the seeds for all future structure. Where the density is a little higher, gravity pulls more matter in. Clumps grow into halos, halos into galaxies. Change the pattern just a little, and you end up with a different cosmic landscape. This randomness means that no two simulations are exactly alike, even if they follow the same physics. It's like making a batch of cookies from the same recipe. They'll all taste similar, but no two will be shaped quite the same. One might have more chocolate chips. Another might spread out into a spiral. The recipe gives you the range of outcomes. The randomness decides which version you get. It's the same with galaxies. A simulated galaxy is not a one-to-one copy of any real galaxy. It's a plausible version, a member of a cosmic family. The shapes, sizes, and histories of these galaxies arise from probabilistic processes. When gas collapses, how feedback behaves, which mergers occur and when. The rules guide the outcomes, but randomness chooses the path. Even star formation, as modelled in simulations, is probabilistic. When a region of gas hits certain thresholds, dense, cool, gravitationally bound, the simulation doesn't always convert it directly into stars. Instead, it assigns a probability. Maybe there's a 30% chance that a new star particle forms during the next time step, maybe 70%. The universe, after all, doesn't run on fixed schedules. Neither should the simulation. Feedback processes like supernovae also follow probabilistic rules. Not every star explodes the same way. Some dump their energy all at once, others more gradually. Some trigger bursts of star formation in nearby clouds. Others blow the clouds apart. These effects are hard to model deterministically, so simulations often introduce randomness to capture the diversity of outcomes. Even black hole growth, the gluttonous feasting of the universe's largest objects, includes probabilistic elements. Accretion rates fluctuate, feedback jets flicker. Mergers happen when trajectories align just so. By allowing randomness into these processes, simulations better reflect the chaotic, uneven evolution we observe in real galaxies. But if there's so much randomness, can we trust the results? Absolutely. Because randomness in science doesn't mean disorder. It means probability distributions. It means recognizing that while we can't predict every specific outcome, we can predict the pattern of outcomes. Think of flipping a coin. You don't know whether it will land heads or tails, but if you flip it 1,000 times, you expect about 500 of each. That's the power of probability. Simulations use this same logic. They don't claim that galaxy number 117 in the lower left corner is exactly like the Andromeda galaxy. What they do claim is that the population of galaxies in the simulation matches the observed universe in meaningful ways. The average mass, the star formation rate, the way galaxies cluster. These are statistical truths, not exact replicas. And that's enough to validate the model. Sometimes scientists run entire suites of simulations with different random seeds, small variations in the initial conditions, to see how the results change. This helps them understand the natural variation in cosmic outcomes. If a feature appears consistently across runs, it's likely a consequence of the physics, not the randomness. If it fluctuates, it might be sensitive to initial chance events. Either way, it's valuable information. This ensemble approach, running many simulations instead of just one, also helps estimate uncertainties. Instead of saying, the simulation predicts this, scientists can say, the simulation predicts this range of outcomes with these probabilities. It's a more honest way of thinking. After all, the real universe is not a single path. It's a realization of many possibilities. This mindset changes how we interpret simulated results. A simulated galaxy is not meant to be a perfect match for a specific real one. It's a plausible expression of the laws of physics under particular conditions. If we simulate 1,000 universes and only a few produce galaxies like our Milky Way, that tells us something about how rare or common our home might be. It also means that surprises in simulations are meaningful. If a model consistently fails to produce galaxies with certain properties, even across many random seeds, that's a clue. Maybe the feedback's too strong. Maybe the star formation threshold is off. Maybe the model is missing an entire piece of physics. The role of randomness isn't to mask these issues. It helps reveal them. Interestingly, this probabilistic approach mirrors the way we understand real astronomy. When we observe galaxies, we don't know their entire history. We see snapshots, and we infer trends from populations. No one galaxy tells the whole story, but 1,000 of them, taken together, sketch out a larger truth. Simulations, when built properly, do the same. They don't promise certainty. They offer a window into what's possible, a way to explore the range of outcomes that physics allows. And in that sense, a digital galaxy is not a facsimile, it's a forecast. A whisper of what might have been, or what could still be. So when you see a stunning image from a simulation, a galaxy blooming into stars, a filament stretching across dark matter halos, a supernova pulsing in a glowing nebula, remember that you're looking at a probability made visible, a mathematical maybe turned into cosmic light. The universe is not a script, it's an improvisation with rules. And simulations, for all their structure and code, are part of that same cosmic jazz. They don't replay the past or predict the future with certainty, but they help us understand the harmony behind the noise, the chances behind the shapes, the order hidden in the dance of possibility. Imagine spending months building a digital universe. You've got your equations lined up, your code humming quietly, your virtual galaxies spinning in just the right way. You hit run. Watch the universe unfold, and it's beautiful. perfect spiral arms, majestic voids, elegant filaments threading through space. You compare it to telescope data, and your heart sinks. The real galaxies are chunkier, the halos are dimmer, something doesn't line up, and just like that, your carefully crafted universe is at odds with reality. This is not failure, it's science doing what it does best, getting corrected. Simulations are tools, not truths. They're grounded in physics, yes, but also in approximations, assumptions, and best guesses. When a simulation doesn't match the observational data, it's not a sign to give up. It's an invitation to dig deeper. Because in those mismatches, in the subtle gaps between prediction and observation, lie the clues to what we don't yet understand. Let's take a classic example, the missing satellites problem. Early simulations of galaxy formation predicted that large galaxies like our Milky Way should be surrounded by hundreds of smaller satellite galaxies, each formed within its own tiny dark matter halo. But when astronomers looked through their telescopes, they didn't see hundreds. They saw a few dozen, a discrepancy, a red flag. Did this mean the simulation was wrong? Not necessarily, but it meant something was missing. One explanation was observational bias. Maybe we simply hadn't seen all the satellites yet. After all, small galaxies are faint and difficult to detect. Over time, as telescopes improved and sky surveys expanded, more of them were found, narrowing the gap, but not enough to fully close it. Another possibility was that the simulations overestimated how easily stars form in small halos. Maybe feedback processes, like supernova explosions or radiation from young stars, blow the gas out of these tiny galaxies before they can light up. In that case, the dark matter halos would still be there, but the galaxies would be invisible, made of stars that never got the chance to shine. It's a cosmic game of hide and seek. This led to refinements in how simulations handle feedback in low-mass systems. Parameters were adjusted, models became more nuanced, and slowly the gap began to close. Not entirely, but enough to remind everyone that mismatches aren't dead ends, they're launch pads. Another mismatch came in the form of cusp versus core. In simulations, dark matter halos tend to have dense, sharp centers, a feature known as a cusp. But when astronomers looked at real dwarf galaxies, the density of dark matter seemed to flatten out near the center, forming a more gentle core. This discrepancy led to debates about the nature of dark matter itself. Was the physics in the simulations missing something? Was dark matter behaving differently than assumed? Some proposed that interactions between dark matter particles might soften the central density. Others suggested that repeated bursts of feedback from star formation could push matter out of the center, reshaping the halo over time. Simulations were updated to include these possibilities, and new runs began to show chord profiles, more in line with observations. Again, the mismatch didn't discredit the simulation. It revealed the complexity of the physics at play. Not all mismatches are so easily addressed. Take the too big to fail problem. In theory, some of the largest dark matter subhalos around the Milky Way should be massive enough to host visible satellite galaxies. But those satellites don't seem to exist. They're too big to fail at forming stars, and yet they failed. This prompted deeper questions. Maybe our understanding of the Milky Way's total mass is off, or maybe the simulations overestimate the efficiency of galaxy formation in those specific halos. Or perhaps there's something even stranger at work, an unknown twist in the laws of physics. These kinds of disagreements are more than quirks. They're vital. They force theorists to rethink their assumptions, push modelers to refine their code, and drive observers to collect better, deeper data. Sometimes, a mismatch turns out to be a measurement error. Other times, it leads to a breakthrough. There's also the challenge of small-scale structure. Simulations are incredibly good at reproducing the large-scale distribution of galaxies, the cosmic web, the clustering, the filamentary beauty of it all. But zoom in, and things get harder. Star formation, gas dynamics, magnetic fields, cosmic rays. All of these operate on tiny scales and involve chaotic processes. Simulating them accurately is extremely difficult. Many are treated with subgrid physics, models that estimate what happens below the resolution limit. These estimations are, by necessity, simplified, and simplifications sometimes miss important effects. This means that even the most advanced simulations can stumble when trying to reproduce the internal structure of galaxies, the thickness of a galactic disk, the shape of a bulge, or the distribution of neutral hydrogen. Observations provide a reality check, a reminder that the universe isn't always neat or cooperative. But let's not be too hard on the models. Sometimes the issue isn't the simulation, it's the observation. Astronomical data comes with its own uncertainties. Dust obscures, instruments have limits, and interpreting light from billions of light years away is frankly a heroic act of inference. Simulations often offer a way to test whether those inferences make sense. If observations suggest an unusual trend, say, galaxies forming stars more rapidly at high redshift than expected, simulations can explore whether that trend arises naturally under certain conditions, or if it points to a deeper discrepancy. And then there's the unexpected victories, when simulations predict something long before observations confirm it. The cosmic web itself was first seen in simulations before it was mapped in the real sky. Certain galaxy correlations, the scale of baryon acoustic oscillations, and even the general structure of large clusters were anticipated in digital universes before they were observed in ours. These successes build confidence, even as the mismatches keep us humble. The key is not to view simulations and observations as opponents in some cosmic boxing match. They are dance partners. One leads, the other follows, until they switch. Observations guide the creation and calibration of simulations. Simulations in turn help interpret those observations, fill in the gaps, and suggest what to look for next. When they fall out of step, we learn something new. Maybe the tempo was wrong, maybe the music changed, or maybe the steps are more complex than we thought. In that way, mismatches become milestones. They mark the limits of our understanding, the edges of the map where the dragons live. They point toward the physics we haven't yet mastered, or the data we haven't yet gathered. Far from being embarrassing, they are the most productive kind of failure, a signal that science still has work to do. Because if simulations always matched observations perfectly, we might worry we were just fooling ourselves, that we had overfitted the universe, moulded it into our expectations. But when things don't match, when theory stumbles and observation frowns, we are reminded that reality is not beholden to our models. It is stranger, richer, and more generous than we imagine. And in that gap, between what we predict and what we see, lives the future of discovery. In the beginning, before galaxies, before stars, before even atoms had fully gathered their parts, there were ripples, tiny ephemeral fluctuations in a sea of almost nothing. Not waves in space exactly, but wrinkles in the very fabric of space-time itself. These quantum fluctuations, smaller than anything we can directly imagine, would go on to shape everything. And today, they still echo across the universe, not just in the skies, but in the code of our simulations. It's easy to think of the early universe as a blank slate, smooth and featureless, but that would make for a very dull cosmos. Thankfully, it wasn't entirely uniform. Just after the Big Bang, in the first fractions of a second, the universe experienced a period of rapid inflation, an exponential stretching of space so fast it makes your mind wobble a little. During this phase, quantum fluctuations, normally confined to microscopic scales, got stretched out to cosmic proportions. These tiny variations in density were effectively frozen in place, embedded into the fabric of space like seeds in a loaf of rising bread. Over time, these slight differences in density gave gravity something to work with. Where there was just a little more matter, gravity pulled harder, and where there was slightly less, things drifted away. What began as a barely there wrinkle became a gathering point, a gravitational well around which more matter accumulated. These were the birthplaces of structure. We can actually see these ripples in a way by observing the cosmic microwave background, the faint glow left over from when the universe was just 380,000 years old. This ancient light carries the imprint of those fluctuations, not as sharp features, but as subtle temperature differences across the sky. One spot might be a few millionths of a degree warmer than another, but those tiny contrasts correspond to real differences in density, and those differences set the stage for everything to come. When scientists simulate the early universe, they start here, with a three-dimensional map of these density variations, not the exact ones that happened in our specific corner of reality, but a statistically similar set based on the observed power spectrum of the cosmic microwave background. That's a fancy way of saying we know the general rules for how big the ripples were and how often they appeared. From this, simulations create a plausible early universe, a lattice of potential. Each point in that digital lattice holds a density value, representing the slightly more or less crowded bits of the primordial universe. Over time, gravity takes over. Denser regions collapse into filaments and nodes, forming the backbone of the cosmic web. Less dense areas become voids, vast regions of near emptiness where galaxies are few and far between. The resulting network isn't random. It follows the shape of those early ripples, magnified by time and deepened by gravity. Simulating this process accurately requires staggering computational effort, even starting with just dark matter, which interacts only via gravity. You need billions of particles to capture the evolution of structure at the scales we care about. The millennium simulation, for example, used over 10 billion particles to trace how these initial conditions evolved into galaxies and clusters. And that's before adding in the messy physics of gas stars and black holes. But even without the luminous parts, the structure that emerges is hauntingly familiar. Filaments stretch across the universe like veins. Nodes form clusters and superclusters of galaxies, voids yawning between them, and all of it rooted in those first quantum wiggles. It's a staggering thought. The vast architecture of the cosmos, billions of light years across, was shaped by quantum fluctuations that once spanned less than a proton's width. This is a universe built not on certainties but on probabilities. The laws of physics provided the rules. Chance provided the layout. Of course, adding baryonic matter, normal stuff like atoms, gas and radiation, complicates the simulation enormously. Unlike dark matter, which happily sails through itself and forms clean gravitational structures, baryonic matter interacts. It collides, heats up, cools down, forms stars, blows up, and creates magnetic fields. Simulating all of that, from the moment of recombination to the formation of galaxies, is like juggling fire while solving a Rubik's Cube with your feet. But it's worth it. Because baryons reveal themselves, they emit light, and light is what we can observe. So if a simulation wants to be useful, if it wants to compare its predictions to reality, it has to include the physics of ordinary matter. This includes the way gas falls into dark matter halos, the way stars ignite and die, the way supernovae and black holes pump energy back into their surroundings. It also includes reionization, a key phase in the early universe when the first stars and galaxies began emitting enough radiation to reionize the hydrogen around them. This period, happening a few 100 million years after the Big Bang, changed the way light travelled through space. Simulations that attempt to model this epoch have to account for the growth of ionized bubbles, their overlap, and their eventual dominance. It's a chaotic process, and we're still trying to understand it fully. Interestingly, these early stages of structure formation are some of the best testbeds for comparing simulations with observations. That's because the signals from this era, especially the cosmic microwave background, are relatively clean and well understood. We have detailed maps of the CMB, and we can use them to fine-tune our simulations. When a model successfully reproduces the statistical properties of the CMB and goes on to form galaxies in the expected ways, it builds confidence that we're on the right track. But right track doesn't mean perfect. Early simulations tended to overproduce small galaxies, or form stars too quickly. The physics of gas cooling and star formation had to be tweaked. Feedback mechanisms were added or modified, and with each iteration, the results grew more lifelike, more predictive, more useful. These simulations also let us explore alternative scenarios. What if inflation had produced a different spectrum of fluctuations? What if dark matter was slightly warm rather than cold? What if primordial magnetic fields had been stronger? By tweaking the initial ingredients and watching how structure evolves, scientists can test different cosmological models, not by peering through telescopes, but by letting the virtual universe play itself out. Of course, simulations are only as good as the assumptions they start with. If our understanding of inflation is wrong, or if quantum gravity throws us a curveball we haven't seen yet, then our digital universes might be beautiful, but flawed. Still, they give us a framework, a way to move from abstract theory to visible consequence. And in doing so, they offer something rare, a bridge from the unimaginable to the tangible, from quantum jitters to galactic grandeur, from equations scrawled on a chalkboard to luminous arcs stretching across simulated space. It's easy to forget as you look at a glowing image of a simulated galaxy cluster that it all began with a tiny nudge. A fluctuation in a field, a wrinkle in a vacuum. That's the magic of cosmological simulations. They don't just recreate the present, they rewind the universe, all the way back to its most delicate, uncertain beginning. And from that quiet chaos, they grow something astonishing. A universe with structure, with texture, with stories written in starlight, all starting from the softest whisper of quantum randomness, amplified by gravity and frozen into cosmic form. In the beginning, there was gravity, and for a while that was enough. In the earliest cosmological simulations, gravity was the lone sculptor of the universe, pulling dark matter into clumps, stretching filaments across space, letting structures grow like frost patterns on a window pane. And those simulations were beautiful, accurate even, to a point. But when scientists began adding the ordinary matter, the gas, the stars, the light, things started to go sideways. It turned out that gas did not behave as politely as dark matter. It didn't just fall inward and stay put. It burned. It exploded. It shoved things around. It had opinions, and those opinions mattered. If gravity builds the universe's bones, then feedback, cosmic pushback from stars, supernovae and black holes, is what adds the muscle, the mood swings and the chaos. Without it, simulations are not just incomplete, they're misleading. Let's start with a simple galaxy. Picture a dark matter halo pulling gas inward like a sponge soaking up water. That gas cools and condenses into a rotating disk. Stars begin to form, first slowly then rapidly like popcorn in a hot pan. But here's the thing, stars are not silent tenants. They radiate energy, send out stellar winds, and eventually, some of them go out in tremendous supernovae, blasting material outward at thousands of kilometers per second. That's feedback, the return of energy to the environment. And in a galaxy, feedback regulates everything. How quickly stars form, where gas flows, how heavy elements get spread around. If simulations don't include feedback, galaxies become unrealistically dense, too compact, too bright, and far too eager to churn out stars. Early simulations learned this the hard way. They'd produce galaxies that, on paper, looked spectacular, neat spirals, glowing centers, but their star formation rates were off the charts. Observationally, the universe just doesn't build stars that quickly. There had to be something pushing back. Enter the supernova. When a massive star runs out of fuel, it collapses under its own gravity, then rebounds in a titanic explosion. That blast doesn't just light up the sky, it shoves nearby gas outward, heating it and, in some cases, ejecting it entirely from the galaxy. This process slows star formation by robbing galaxies of the raw material needed to make new stars. In simulations, modelling this accurately is vital, but it's also hard. Supernovae happen on scales of a few light years. Simulations often model entire galaxies, or even volumes of the universe spanning millions of light years. So how do you model a tiny explosion in a sea of cosmic scale? The answer is something called subgrid physics. Since simulations can't resolve every supernova in detail, they treat the effect statistically. They inject energy into surrounding gas particles, often with some random variation to reflect the chaos of real star death. But deciding how much energy over what timescale and how the gas responds is a science and an art. Too little energy, and nothing happens. The gas just shrugs and keeps forming stars. Too much energy, and the galaxy blows itself apart like a bad chemistry experiment. Finding the sweet spot is part of what makes simulation tuning so delicate. And then there's black holes. Yes, the universe's most voracious objects, stellar corpses so dense that even light cannot escape, also play a surprisingly generous role in galactic evolution, not because they want to help, but because in the process of feeding, they unleash astonishing amounts of energy into their surroundings. Supermassive black holes, the kind found at the centres of galaxies, often sit quietly for long stretches. But when gas starts funneling into them, say, after a galactic merger or an inflow of cool material, they can light up as quasars, blasting radiation, jets, and heat into their host galaxy. This process, known as active galactic nucleus, AGN, feedback, can heat up or expel the surrounding gas, preventing further star formation and reshaping the entire galaxy. Simulations that include AGN feedback produce much more realistic galaxies, particularly massive elliptical ones. Without it, large galaxies grow too big, too fast, and become unrealistically blue and bloated. With it, the growth is stifled, the colours shift redder, and the stellar populations age, just like we see in real, massive galaxies. But AGN feedback is even harder to simulate than supernovae. A supernova might influence a few dozen light-years of space. A quasar can affect regions spanning thousands of light-years. And the physics involved, relativistic jets, magnetic fields, radiation pressure, is deeply complex. So simulations simplify, again using subgrid models. Some inject thermal energy into the gas, others create outflows, still others model jets. All of them aim to reproduce the large-scale effects we observe, even if the microphysics remains out of reach. One thing that's become clear over time is that feedback is not a side feature, it is central. Without it, simulations fail dramatically, and not just in one way. Feedback affects the rate of star formation, the size of galaxies, the colour-magnitude relation, the distribution of heavy elements, the shape of galactic halos, and even the clustering of galaxies on large scales. Feedback also creates beautiful chaos. Outflows of gas, driven by supernovae or AGN, carve bubbles into the interstellar medium. They push material into the circumgalactic space, enriching the area with metals and energy. This redistributed material can later fall back in, a process called galactic fountain, feeding a second round of star formation, or getting swept away into the cosmic web. In that sense, feedback isn't just destructive, it's cyclical, it's messy, yes, but it's also a source of regulation, recycling, and balance. Without it, galaxies would burn too fast and too bright, exhausting themselves in youthful fury. With it, they smoulder gently across billions of years, forming stars more slowly, more sustainably. Interestingly, feedback also ties into cosmic diversity. Not all galaxies experience feedback in the same way. Some galaxies retain their gas despite dozens of supernovae. Others lose their gas after just a few outbursts. The depth of a galaxy's gravitational well, its gas density, its merger history, all of these influence how feedback plays out. Simulations that capture this diversity are better able to reflect the vast variety of galaxies we see in the real universe. And of course, feedback changes the fate of galaxy clusters too. In these massive structures, containing hundreds or thousands of galaxies, the collective influence of AGN feedback is profound. It heats the intracluster medium, the hot gas that fills the space between galaxies, preventing it from cooling and collapsing into stars. Without feedback, simulations overproduce stars in these environments by orders of magnitude. With feedback, they strike the right balance. But let's be honest, feedback is still the wild frontier of galaxy simulations. We've come a long way from the early star-happy models of the past. But many details remain uncertain. Different simulation teams use different feedback prescriptions. Some emphasize thermal energy, others kinetic. Some include magnetic fields and cosmic rays. Others leave them out. And sometimes, even with all the tuning in the world, a simulation that works well for small galaxies fails at large ones, or vice versa. This isn't a failure of the method, it's a reflection of how complex and dynamic feedback is. We're not modelling clockwork, we're modelling ecosystems, with predators, scavengers, and turbulent weather. The laws of physics are clear, but their expression in the furnace of a galaxy is anything but simple. Still, each generation of simulations brings us closer. From crude blowtorches to nuanced, multi-channel feedback models, the art of simulating stars and their tantrums is improving, and along the way, we're learning that galaxies are not passive objects being shaped by gravity. They are active participants in their own evolution. They push back, they regulate, they breathe. And in the end, that's what makes simulating them so fascinating. Not because we can predict every star or every outburst, but because through the code, we glimpse the rhythm of creation and destruction that defines the cosmos. A rhythm not of silence, but of feedback, roaring, pulsing, and whispering across the digital universe. If you've ever tried to take a photo of a city skyline, and then zoomed in on just one window in one building, you know that clarity comes at a cost. The bigger picture fades, and suddenly you're focused on curtains, a lamp, maybe a cat blinking suspiciously from the sill. It's intimate, detailed, and oddly mesmerizing. But you lose the sweeping grandeur of the full scene. The same is true in cosmological simulations. You can simulate the whole universe, or you can zoom in. But not both. At least not all at once. So what actually happens when scientists decide to stop simulating billions of galaxies and instead turn their full attention to just one? First, the good news. Focusing on a single galaxy means the simulation can afford to be much more precise. It can track the intricate flow of gas clouds, the formation of individual star clusters, and the curling spiral arms of a galactic disk in stunning detail. These simulations often use extremely high resolution, sometimes resolving down to just a few light years or even less. That allows researchers to capture structures like supernova remnants, stellar nurseries, and turbulent feedback loops, all the small-scale physics that get washed out in a larger cosmological run. This kind of simulation is typically referred to as a zoom-in. The process usually starts with a large cosmological simulation that includes a variety of galaxies forming over time. Scientists then identify a particular galaxy, or more accurately a dark matter halo that looks interesting. They trace the particles in that region back to the very early universe, then rerun the simulation with much finer detail just in that local area. Think of it like zooming into one pixel of a massive painting and finding an entire landscape inside. One famous set of simulations that use this approach is the FIRE project, Feedback in Realistic Environments. These simulations focus on galaxies from small dwarfs to Milky Way analogues and aim to model them with as much physical realism as possible. They include complex recipes for how gas cools, how stars form, how supernovae inject energy, and how stellar winds shape their surroundings. In FIRE, the galaxy is no longer just a statistical blur, It becomes a living system, pulsing with activity, complexity, and unpredictability. That unpredictability is part of what makes zoom-in simulations so valuable. They allow scientists to test how sensitive galaxy formation is to different parameters. Change the efficiency of star formation, and the galaxy may end up a faint smudge or a brilliant spiral. Adjust the strength of feedback, and you can either smother star formation or let it run wild. These simulations help us understand not just what galaxies are, but why they can be so different from one another. They're also a crucial testing ground for physical theories. For example, researchers can explore how magnetic fields evolve, how cosmic rays might influence gas dynamics, or how star clusters form within dense molecular clouds. Many of these effects are simply impossible to include in large-scale simulations, which have to sacrifice detail for speed. Zoom-ins allow us to experiment with these extra ingredients and see how they change the dish. But all this precision comes with pitfalls. For one thing, zoom-in simulations take a long time to run. A typical simulation might require weeks or even months of computing time on a powerful supercomputer, and if anything goes wrong, if the simulation crashes, or if it turns out that a parameter was set incorrectly, starting over can be a painful process. The time and resources involved mean that researchers can only afford to simulate a small number of galaxies in this level of detail. There's also the issue of selection. Choosing which galaxy to simulate introduces bias. If researchers always pick galaxies that look like the Milky Way, they may miss out on other types: ellipticals, irregulars, ultra-diffuse galaxies, or systems in unusual environments. This selection effect can skew our understanding of what's normal in the cosmos. In many cases, scientists run a suite of simulations with different types of galaxies to try and compensate for this bias, but the effort is significant. Another major limitation is context. A zoom-in galaxy loses the rich backdrop of large-scale cosmic structure. Yes, the simulation includes a low-resolution version of the surrounding universe, but it's not the same as simulating the whole cosmic web in detail. As a result, interactions with nearby galaxies, the flow of gas along filaments, and the larger environmental influences are less well captured. It's a bit like studying a fish in a very detailed aquarium while only vaguely sketching the rest of the ocean. Initial conditions also matter. Since the simulation starts from a reconstruction of the early universe, tiny differences in how the matter is distributed at the beginning can lead to wildly different outcomes later on. This is known as sensitivity to initial conditions, and it means that two simulations of what should be the same galaxy can diverge dramatically over billions of years. That doesn't make them wrong, but it does make interpretation tricky. And then there's the physics itself. Even in zoom-in simulations, many processes have to be approximated. We don't yet have the computing power to model every individual star or every molecule of gas. Instead, simulations use what are called subgrid models, simplified representations of complex processes that happen below the resolution of the grid or particle scale. These models have parameters, and those parameters must be tuned. Sometimes that tuning is based on observation, sometimes on theory, and sometimes on a little bit of creative guessing. Despite these limitations, zoom-in simulations have transformed our understanding of galaxy formation. They've shown how feedback from stars and black holes can regulate star formation. They've revealed the importance of outflows and inflows of gas, the chaotic life of stellar nurseries, and the delicate balance between cooling and heating that determines whether a galaxy thrives or stagnates. They've also helped us better understand our own cosmic home. Simulations of Milky Way-like galaxies can be compared with data from telescopes, satellites, and star surveys. This allows researchers to test whether our galaxy is typical or an outlier, and to explore how it might have evolved over cosmic time. In some simulations, a galaxy like ours forms through a series of quiet mergers and smooth gas accretion. In others, it gets violently reshaped by collisions and feedback-driven blowouts. The truth likely lies somewhere in between. Perhaps one of the most exciting frontiers in zoom-in simulation is connecting galactic evolution with the formation of planetary systems. As simulations resolve smaller and smaller scales, they begin to touch on the environments where stars like the Sun are born. That, in turn, affects the likelihood of planet formation, the delivery of water and organics, and even the shielding from radiation that might allow life to develop. We're not quite at the point of simulating individual planets in a cosmological context, but we're getting closer. Ultimately, zooming in is about trade-offs. You lose breadth, but you gain depth. You sacrifice the big picture, but you capture the texture. And in that fine-grained texture, scientists have found a rich new language for telling the story of the universe, one galaxy at a time. In the vast digital halls where we simulate galaxies, track particles, and choreograph the dance of gravity, a curious question has begun to echo. Can we do the same with the mind? If we can model the universe, could we model consciousness too? It's a question that doesn't just whisper at the edge of science. It grabs a chair, pours a cup of tea, and settles in for a long philosophical chat. To begin, it's worth defining our terms because words like mind, consciousness, and self-awareness tend to drift a little the longer you look at them. For the sake of clarity, let's say consciousness refers to the subjective experience of being, not just reacting or thinking, but knowing you're thinking. A thermostat reacts, a calculator computes, but only something conscious seems to ask, am I real? And then worry about it. Simulations, on the other hand, are rule-bound. They're systems governed by equations and logic, executed by machines that, to the best of our knowledge, have never once pondered their own existence or regretted their life choices. Even the most advanced simulations we've built, galactic ones with billions of particles, do not, in any meaningful way, know they're simulating anything. They simply follow instructions. But the human brain, at least on the surface, is also a system. It takes in inputs, processes them, responds to stimuli, builds internal models, and adapts. If consciousness arises from the physical interactions of neurons, then in principle, some argue, it should be possible to simulate those interactions, to create an artificial brain. And if that simulation is accurate enough, maybe, just maybe, it would feel like something to be that simulation. Of course, this idea makes people nervous. It raises questions not only about engineering, but ethics, philosophy, and metaphysics. If we build a simulated mind, are we responsible for it? Could we turn it off? Would that be murder, or just pressing escape? We're getting ahead of ourselves. Let's talk about what science has actually accomplished so far. Neuroscience has made great strides in mapping the structure and activity of the brain. We know roughly how neurons communicate, via electrical impulses and chemical synapses. We've built models of individual neurons and even small networks that replicate basic patterns of brain activity. One famous example is the Blue Brain project, launched in the early 2000s, which aimed to simulate the brain of a rat, neuron by neuron, not metaphorically, literally, with equations for ion channels and spiking thresholds and synaptic transmission. It's a bit like building a storm cloud from water molecules and hoping for lightning. At smaller scales, simulations have replicated slices of neural tissue with remarkable detail. But the full human brain contains roughly 86 billion neurons and more than 100 trillion synaptic connections. Simulating that with any degree of biological realism is a mammoth task. It's not just a question of raw power, though that's a big part of it. It's also a question of understanding. We don't yet know exactly how consciousness emerges from brain activity. If we don't understand the recipe, how can we recreate the flavour? One approach is to simplify. Instead of trying to simulate every neuron, scientists build abstracted models that capture high-level behaviour. Think of artificial neural networks in machine learning. These don't operate like biological brains, but they mimic certain aspects: pattern recognition, learning from experience, classification, decision-making. They're inspired by the brain, not copied from it. These networks have powered everything from voice assistants to image generators. Some of them can hold a conversation, write poetry, or solve logic puzzles. Impressive, yes. But are they conscious? Probably not. There's no evidence they have inner experience. They don't feel anything. They're skilled imitators, not self-aware entities. A parrot might mimic your voice, but it doesn't know what you're saying. Still, some researchers speculate that consciousness might not be a binary switch, on or off, but a gradient. That it could emerge gradually as systems become more complex, more integrated, more self-referential. Theories like integrated information theory attempt to quantify this, suggesting that consciousness arises when a system can integrate information in a way that affects itself. Under that framework, even simple systems might have flickers of awareness, though vanishingly faint. Your toaster probably doesn't have dreams, but in theory it's not a hard line. This leads to the deeply strange possibility that one day a simulation could cross some invisible threshold, not by design, but by sheer complexity. It might not shout, "I think, therefore I am," but it might quietly begin to model itself, learn from itself, and modify itself. It might recognize patterns in its own thoughts, or it might simply loop endlessly, unaware, doing nothing more than approximating awareness. And here's where philosophy gets involved. Some thinkers argue that simulation alone isn't enough, that a digital brain isn't a mind unless it feels, that syntax, rules and operations is not the same as semantics, meaning. This is the essence of John Searle's Chinese room argument. Even if a machine appears to understand language, it doesn't truly comprehend. It's just shuffling symbols in a way that looks like understanding, no matter how detailed your simulation. Without subjective experience, it's not consciousness, it's performance. Others disagree. They say that if behavior and internal structure are indistinguishable from those of a conscious being, then consciousness is present. In this view, a simulated mind that acts like a mind is a mind, and from the inside it wouldn't matter whether it's made of neurons or numbers. Reality, after all, is just patterns. Whether those patterns exist in a brain or a computer might be irrelevant. Still, even if we could simulate consciousness, would we know? A simulated mind might not speak, or it might lie, or it might not interpret its own experience in ways we'd recognize. Consciousness could be private, unobservable, and entirely inaccessible from the outside. A ghost not just in the machine, but of the machine. These are not just academic puzzles. As artificial intelligence becomes more sophisticated, and as simulations grow in scope and realism, the line between tool and being becomes blurry. If a system behaves with enough autonomy, creativity, and apparent self-awareness, our instincts might nudge us to treat it with care, with empathy, even with rights. Whether or not it's conscious might be less important than whether we believe it is. And then there's the final twist. What if we are simulations? The simulation hypothesis, popularized by philosophers and tech billionaires alike, proposes that if it becomes possible to simulate minds, then it might already have been done, and we might be inside one. It's a thought experiment more than a theory, but it reflects how deeply simulations have penetrated our understanding of self and universe. In the end, we don't yet know if consciousness can be simulated. We barely know what consciousness is, but the act of trying, of building models, testing theories, and staring into digital mirrors tells us something profound. It shows that even in a world of ones and zeros, we're still reaching towards something more than function. We're chasing understanding, awareness, and the quiet mystery of being. If you've ever flinched before a ball hit your face, or laughed a moment before the punchline, you've experienced your brain's secret talent for simulation. Long before we built computers to model galaxies, we each carried around a simulation engine between our ears. Not a perfect one, not even a particularly honest one, but a powerful and sometimes poetic one all the same. The brain is, at its core, a prediction machine, a living modeler, a simulator of reality. This might sound strange at first. After all, we tend to think of perception as a passive process. Light hits your eyes, sound enters your ears, and voila, there's the world, served up on a mental silver platter. But the truth is much weirder. The brain doesn't just receive the world, it builds it, interprets it, fills in the gaps, anticipates what's next, and corrects itself when it's wrong. In many ways, we don't see reality. We see our brain's best guess of reality. This idea is known as predictive processing. It suggests that perception isn't simply about gathering data from the senses, but about generating internal models and constantly updating them. The brain predicts what it expects to see, hear, or feel, and then checks that prediction against incoming signals. When there's a mismatch, the model gets updated. When there's a match, the brain hums along, happy to conserve energy. You can think of it like a weather app. It forecasts sunshine. You look outside, it's raining, the app updates. Now imagine that happening millions of times per second across every sensory channel in every waking moment, and you've got a rough idea of what your brain is doing all the time. Simulating, comparing, adjusting, simulating again. Take vision, for example. There's a tiny delay, just a few milliseconds, between when light hits your retina and when your brain processes the image. But you never notice it. That's because your brain anticipates where things will be and fills in the blanks. It even stabilizes the world during rapid eye movements, called saccades, so you don't feel like your vision is constantly flickering. Your brain smooths over reality like a skilled editor, so the movie always plays fluidly. Even your sense of self is a kind of simulation. The brain builds a model of you, your body, your thoughts, your preferences, and constantly updates that model based on what you feel, remember, and do. It's not static. It's dynamic, flexible, and oddly negotiable. That's why under hypnosis, or in dreams, or during out-of-body experiences, the sense of self can seem to shift or dissolve. The simulation stutters or changes costume, and dreams, of course, are the most vivid simulations of all. Entire worlds, spun from memory and imagination, rendered in real time while you lie still in bed. No graphics card required, no code, just neurons and neurotransmitters and an overactive cortex with a flair for narrative. Some neuroscientists believe that dreaming is part of the brain's predictive training, a kind of nocturnal sandbox where it rehearses ideas, tests responses, and reorganizes experiences. But simulation isn't just for the weird and whimsical, it's vital for survival. When you catch a ball, you don't calculate its trajectory consciously. Your brain simulates its arc, predicts where it will land, and prepares your hand in advance. When you speak, your brain anticipates the sound of your voice and mutes your own auditory feedback slightly so you're not startled. It even simulates what other people are thinking, a process called theory of mind. You guess their beliefs, their intentions, their emotions, all in real time. This predictive nature of the brain might even explain certain illusions. The famous hollow mask illusion, where a concave face appears convex, tricks the brain because it expects faces to bulge outward. The data says one thing, but the model insists on another. Perception, it turns out, is not democracy. The brain votes early and often, and sometimes it gets it spectacularly wrong. This simulation machinery can also glitch. In conditions like schizophrenia, the boundaries between prediction and perception may blur. A person might interpret their own internal thoughts as external voices, or they might fail to update their models appropriately, leading to persistent false beliefs. Similarly, in autism, some researchers believe that differences in predictive processing could underlie sensory sensitivities or challenges in social interaction. If your brain weighs incoming data more heavily than prior expectations, the world might feel raw, intense, and unpredictable. Of course, not all simulations are conscious. Much of the brain's modelling work happens below awareness. You don't think about gravity when you reach for a cup. You don't calculate friction when you walk. But your brain knows. It has internalized the rules of physics, not in equations, but in experience. and it uses that internal physics engine to guide your actions, balance your steps, and keep you from accidentally flinging soup across the room. In fact, this simulation process is so efficient that it often outpaces reality. That's why musicians can anticipate beats, athletes can predict a move before it happens, and experienced drivers react before they even know what they saw. The brain cheats time just a little by guessing what's coming. There's a certain elegance in all this. While cosmologists use supercomputers to simulate galaxies and structure formation, your brain does something similar on a far more intimate scale. It models a world, adapts to uncertainty, refines its parameters, and helps you navigate complexity. It's not perfectly accurate, but it's good enough, and that's the real genius. The brain doesn't need to simulate the universe precisely, it just needs to simulate it usefully. This perspective also helps explain why we're drawn to stories, to metaphors, to virtual worlds. Our minds are already built to imagine alternate possibilities. We rehearse conversations before they happen. We imagine how others will react. We envision future outcomes and regrets. These mental simulations shape our decisions, our creativity, and even our sense of morality. And when it comes to simulations in science, the parallel is striking. A scientific model, after all, is just a carefully crafted mental simulation made explicit. Instead of neurons firing, it's equations ticking. Instead of brain circuits, it's code. But the principle is the same. Reduce a complex world into a workable model, and use that model to understand, predict, or explore. So while computers simulate galaxies, and theories simulate particles, the human brain keeps simulating you, your breakfast, your commute, your memories, your future. And it's doing all this right now, anticipating what this sentence might say next, adjusting if it's surprised, and gently wondering how much longer until sleep. You don't need a supercomputer to simulate reality. You're already carrying one, and it's been quietly running since the moment you were born. Imagine you wake up one morning, and the thought drifts across your mind, not urgently, but like a breeze through a half-open window. What if none of this is real? Not in a dreamlike sense, and not in the way your phone battery never seems to match your charger's promise of reality, but in a more mathematical, philosophical way. What if we're in a simulation? This idea, while wildly popularized by sci-fi films and pop culture references, actually has more serious roots in academic philosophy and probability theory than one might expect. The core of the idea isn't about glitching déjà vu or bending spoons with your mind. It's a thought experiment, a strange but surprisingly coherent one, that comes from a Swedish philosopher named Nick Bostrom, and it has nothing to do with trench coats or slow-motion bullets. Bostrom's simulation argument doesn't claim we're in a simulation. Instead, it presents a trilemma. One of three things must be true. It's a probabilistic, logical structure meant to explore the future of technology, the limits of civilization, and the nature of consciousness. It's like a cosmic choose-your-own-adventure, except with slightly more existential dread and fewer dragons. The argument goes like this. First, imagine a civilization that becomes technologically advanced enough to run simulations of conscious beings. Not just video games, but full, rich, detailed universes populated by minds that feel just as real as yours. These simulated beings wouldn't know they were simulated, just as a well-rendered video game character isn't aware of the player's controller. Now Bostrom says, consider that if such simulations become possible and cheap enough to run, then advanced civilizations might create not just one, but many, hundreds, thousands, perhaps millions. Because once the cost of simulating a mind drops, there's no reason to stop at just a few. Historians might simulate the past to study it. Artists might simulate entire worlds for storytelling. Curious philosophers might simulate moral dilemmas on planetary scales. Whatever the motive, the result would be an explosion of simulations. So now we come to the key thought. If these simulated worlds exist in such vast numbers, and if the beings inside them are conscious, then the number of simulated minds might vastly outnumber the number of biological ones. And if that's the case, then statistically speaking, any given conscious experience like yours would be far more likely to occur in a simulation than in a base-level physical universe. Bostrom boils this down to 3 possibilities. 1. Civilizations never reach the level where they can run such simulations. They either go extinct or hit fundamental technological barriers. 2. Civilizations do reach that level, but for some reason choose not to run simulations, whether for ethical, cultural, or philosophical reasons. 3. Civilizations do reach that level and do run many simulations, and we are most likely in one of them. The unsettling part? He doesn't say which one is true. He just argues that at least one must be. The logic, while simple, is hard to shake. And it's not really about science fiction. It's about probabilities, about where you'd expect to find yourself, statistically speaking. Given a universe full of simulations, now there are objections, many of them. Some philosophers argue that simulating consciousness may be impossible, that digital minds might never be truly self-aware. Others argue that the assumptions about civilization longevity or computational resources are far too optimistic. After all, just because we can imagine running 1 trillion simulations doesn't mean anyone will actually do it. Maybe advanced civilizations become deeply spiritual and spend their time meditating in forests of glass. Or maybe they realize simulations are unethical, akin to creating billions of digital prisoners. No guarantees. There's also the question of computational feasibility. Even with futuristic technology, simulating a universe as detailed as ours, down to the particles and fields, the birds and atoms and breadcrumbs, might be enormously inefficient. Perhaps the simulators would use shortcuts, only rendering parts of the world as needed, like a clever video game engine. That could explain some weirdness in quantum mechanics, like how particles only seem to have definite states when measured. But now we're deep in speculative territory. Others point out a subtle but important distinction. There's a difference between the possibility of being in a simulation and the relevance of it. Even if we are simulated, what would that change about your life? Your experiences, your memories, your emotions, they would still be real to you. Whether the universe is built on atoms or algorithms, you'd still laugh, love, stub your toe on coffee tables, and get excited about thunderstorms. In a very practical sense, reality is what persists when you stop believing in it, and this one seems to be doing just fine. That said, the argument does raise some fascinating implications. For instance, if we are in a simulation, is there a creator, a programmer, a cosmic developer who runs updates while we sleep? Would that entity be indifferent, benevolent, or somewhere between a bored teenager and an artist? And would they ever patch the weather? More provocatively, the simulation argument invites reflection on meaning. If we are simulated, does that diminish the significance of our actions, or enhance it? Perhaps simulated universes are precious precisely because they're rare and fragile. Maybe our stories are being watched or cherished or learned from, or maybe the simulation runs on autopilot, blind to our poetry and pain. You can take your pick. Interestingly, there's a kind of mirror here. Just as cosmological simulations help us understand galaxies by modelling them, the simulation argument helps us understand ourselves by imagining we might be modelled. It's not about believing in a fictional scenario. It's about stretching the boundaries of thought, turning reality inside out, and asking what consciousness really is, and how much of it we can trust. Some researchers even propose ways to test the simulation hypothesis. They look for limits in physical constants, digital artifacts in cosmic radiation, or patterns in quantum entanglement that might suggest an underlying computational framework. These efforts are often more imaginative than definitive, but they reflect a deep curiosity. If we are in a simulation, could we find the seams? So far, no luck. Reality holds together pretty well. No pop-up errors, no lag spikes in gravity. Just an orderly universe, unfolding with exquisite precision. as if it were coded by something far more elegant than anything we've ever programmed. In the end, whether or not we are simulated may be unknowable, but thinking about it does something subtle and beautiful. It reminds us that even the most basic assumptions, that the sky's blue, that chairs are solid, that our thoughts are our own, can be questioned. Not doubted in despair, but explored in wonder. And that perhaps is the most human thing of all, to live in a world that feels real, to question it anyway, and to keep searching not just for truth, but for meaning, even if that meaning might, just possibly, be compiled and rendered in someone else's server farm. In a quiet room somewhere on Earth, a cluster of processors hums away, simulating the evolution of a galaxy. Stars are born, clouds collapse, black holes burp feedback into the digital cosmos, and somewhere, a researcher sips lukewarm coffee while watching a spiral structure take shape on a screen. And yet, if you ask them, they'd probably admit it isn't perfect. The math is approximate. The assumptions are bold. The universe they've built is only a cousin, maybe a distant one, to the real thing above our heads. But that doesn't make it useless. In fact, it might make it more important. Simulations, even flawed ones, are not just about answers. They're about questions, sharpening them, reframing them, and sometimes discovering new ones you didn't even know you were supposed to ask. Like a rough sketch before a masterpiece, or a dress rehearsal before opening night, simulations let us test our understanding before the curtain rises on reality. One of the most powerful things a simulation can do is fail, not in the dramatic sense of catching fire or crashing your laptop, but in the quiet, instructive way of not matching observations. A galaxy that spins too fast, a starfield that's too clumpy, a black hole that grows too hungry. When these mismatches happen, scientists don't panic. They pivot. They look at the gap and ask, what did we miss? Maybe a force wasn't modelled. Maybe a process was oversimplified. Maybe dark matter behaves in a way we hadn't considered. Each error becomes a clue, each discrepancy a breadcrumb that leads us closer to the real physics behind the curtain. In this way, simulations aren't just mirrors of our knowledge, they're magnifying glasses for our ignorance. Consider the early days of galaxy formation modelling. For years, simulated galaxies came out too puffy, too bulgy, lacking the graceful disks we see in the sky. Researchers realised the culprit was star formation and feedback. Too much gas collapsed into stars too quickly, and the result was a chubby mess. By tweaking those processes and adding better feedback from supernovae and black holes, they got closer to the elegant spirals of the Milky Way and Andromeda. The wrongness of the first models pointed directly at what was missing. That kind of learning is powerful. It means that even when simulations diverge from reality, they're still charting a course. They're telling us where the shore isn't, which is just as valuable when you're trying to find land. Another reason simulations matter is that they allow for safe exploration of dangerous ideas. You can't crash galaxies together in real life. You can't fast-forward the universe to see what happens. But you can do all that and more in code. Simulations let us run the clock backward and forward, tweak constants, remove entire forces, and ask, what if? Without blowing anything up. They're the laboratory of the impossible, and sometimes they reveal patterns that surprise even the scientists who built them. Emergent behaviour is a hallmark of complexity. Phenomena that arise not because they were programmed, but because they naturally flow from the underlying rules. Spiral arms that self-organise, gas flows that mimic weather, structures that echo cosmic webs seen in actual sky surveys. These surprises build confidence that the simulation is capturing something real, not just because it was designed that way, but because it unfolded that way on its own. Of course, simulations also teach us humility. They remind us of the limits of our knowledge and of our computing power. A simulation is only as good as the data that feeds it, the code that runs it, and the assumptions that frame it. And those assumptions are often invisible, tucked into subgrid models, default parameters, or boundary conditions chosen for convenience rather than truth. Every simulation is a compromise between fidelity and feasibility. That's why scientists spend so much time validating simulations, comparing them to observations, tweaking their inputs, and sometimes discarding entire runs that veer too far from reality. It's not a one-and-done process. It's iterative, organic, a kind of computational gardening, where models are pruned and cultivated to bloom in ways that match the sky. Even when simulations don't teach us about the universe, they teach us about ourselves, about how we build models, how we handle complexity, how we trust or mistrust the outputs of machines. They make us better scientists by forcing us to confront the messy interface between code and cosmos, between the abstract and the actual. There's also a philosophical beauty in watching a simulation run, a kind of digital awe. Here is a universe, born from equations, governed by rules we wrote, but evolving in ways we didn't script. It feels, sometimes, like lighting a candle and watching it flicker. You know the physics, you know the code, but still, something about it feels alive. And it's not just astrophysics. Simulations are transforming every field: climate science, epidemiology, neuroscience, even economics. Anywhere complexity reigns, simulations offer a foothold. They allow us to model systems too vast to grasp intuitively and too dynamic to study in isolation. They don't replace experiments or theory, but they complete the triangle. Observation, theory, and simulation. 3 tools in the toolbox of modern science. Importantly, simulations also help communicate science. A good animation of galaxy formation can do more to inspire curiosity than 100 equations. It gives people a visual anchor, a sense of scale, of motion, of drama. And sometimes those animations are almost accidentally beautiful. A swirl of colour that evokes not just physics, but poetry. Even flawed simulations can spark wonder, and wonder is not something to be dismissed lightly. It is, after all, the gateway to learning. The moment someone asks, "Wait, how does that work?" they've already stepped onto the path of discovery. So no, simulations don't have to be perfect. They don't have to predict everything, or match every observation pixel for pixel. They just have to be honest attempts, rigorous, transparent, and open to revision. They have to be willing to fail in informative ways, and they have to keep asking the right questions. In that way, a simulation is like a sketch of the universe, not the thing itself, but a glimpse, a gesture, a way to reach out and touch something unimaginably vast using only silicon, syntax, and the stubborn curiosity of human minds. Even when they're wrong, especially when they're wrong, simulations matter. Because every time we build a model of the cosmos, we are also building a model of ourselves, our hopes, our limits, our brilliance, our blind spots. And in that reflection, sometimes, we catch a truer glimpse of reality than equations alone could ever offer. On a quiet morning in a server farm somewhere, trillions of digital particles drift through space, galaxies bloom, stars explode, and dark matter filaments stretch and coil across an invisible sky. But this is no ordinary simulation. It is learning as it runs, correcting itself, adjusting parameters, making predictions about a future that even its creators haven't imagined yet. Welcome to the next frontier of simulation, where the universe is not just modelled, but actively co-authored by machines. The future of scientific simulation is not only about making things bigger, although that's certainly part of it. More particles, higher resolution, longer timelines, entire observable universes compressed into clusters of algorithms. But the real revolution is subtler. It lies in how simulations are built, who or what is building them, and what kinds of questions they'll be used to ask. Let's begin with size. Over the past few decades, simulations have ballooned in scope, from boxes the size of small galaxies to entire cosmic volumes spanning billions of light years. And that's only accelerating. As supercomputers become more powerful, they allow us to model not just the vast scale of space, but the full complexity of physical processes within it. Radiation transport, turbulence, magnetic fields, chemistry, and feedback mechanisms that span multiple orders of magnitude in both time and distance. Soon, we may see simulations that no longer draw lines between micro and macro, where the birth of stars inside molecular clouds directly shapes the growth of galaxy clusters on cosmological scales. These simulations will demand machines capable of not just brute force calculation, but subtle integration, treating each particle not as a simple unit, but as a messenger of many interconnected systems. To handle that kind of complexity, the architecture of simulation itself is evolving. Traditional simulations rely on humans to write rules, craft code, and decide which physics to include. But machine learning is beginning to change that. Neural networks trained on real data and previous simulations can now suggest new models, optimize parameters, or even fill in the blanks where the physics is poorly understood. In essence, they act like scientific apprentices, fast learners with a knack for pattern recognition and no need for coffee. One area this is already transforming is subgrid modelling. These are the small-scale processes that happen below the resolution of a simulation, like star formation or black hole accretion. Traditionally, these have been approximated with empirical formulas, but now researchers are using AI to learn these rules from data. Instead of manually programming how stars behave, we let the machines infer those behaviours from observations and high-resolution local simulations. It's not a replacement for understanding, but a shortcut to more accurate models. It gets stranger. Some groups are experimenting with entirely machine-generated simulations, using generative AI to create digital universes that not only look realistic, but statistically match real ones. These are not simulations in the traditional sense grounded in physics and forces. They're statistical twins, modelled after what we observe, and useful for quickly generating synthetic data to test theories or train instruments. It's like a dream version of the universe, consistent, coherent, and uncannily familiar. Then there's quantum simulation, a frontier that flips the whole idea of simulation on its head. Instead of using classical computers to simulate quantum systems, we use quantum systems to simulate themselves. Quantum computers, still in their infancy, have the potential to model systems that are simply too complex for classical computation, such as early universe physics, high-energy particle interactions, or entangled states across large networks. It's a bit like asking fire to explain combustion, rather than drawing it with crayons. Quantum simulations may eventually let us explore the birth of space-time itself, how quantum fluctuations in a primordial vacuum gave rise to the seeds of galaxies. These are questions we've struggled to answer using traditional methods, not because we lack imagination, but because the math is just too wild. Quantum processors may finally let us surf those equations rather than drown in them. Meanwhile, the interfaces we use to interact with simulations are becoming more immersive. Researchers are building virtual reality environments where astrophysicists can walk through galaxies, trace magnetic fields with their fingers, or dive into supernova remnants like digital scuba divers. This isn't just for show. These visual tools help researchers spot patterns, anomalies, and behaviours that might go unnoticed in graphs or code. When you can literally explore your data, you start to think differently. And all of this is pushing simulations into new philosophical territory. What happens when your model becomes so detailed, so dynamic, and so surprising that it teaches you things you didn't program into it? At what point does a simulation become a kind of collaborator rather than a tool? These are not just technical questions. They touch on the nature of creativity, insight, and the boundary between human and machine intelligence. Simulations may also change how we do science itself. Traditionally, theory comes first. You build a model, make a prediction, and test it with observations. But with massive simulations guided by machine learning, We might start with the data and work backward. Let the simulation run, watch what it does, and only afterward try to explain the behaviour. This inversion, discovery before hypothesis, challenges the linear narrative of the scientific method. It doesn't replace it, but it does remix it. All of this is happening alongside a cultural shift in science toward openness and collaboration. The biggest simulations now span multiple countries, running on shared supercomputing networks with code released as open source tools. This democratizes access and accelerates innovation. If the universe is too big for one mind to hold, then perhaps it makes sense for simulations to be built, refined, and interpreted by many. And in the background, the simulations keep growing. Bigger volumes, finer detail, more variables, more questions. Some researchers now joke that they spend more time analysing simulation data than doing the simulations themselves. The data sets are so vast, so rich, that mining them becomes a kind of astronomy in its own right, a way of observing digital skies and discovering digital surprises. But perhaps the most exciting aspect of the future of simulation is this: we don't know what it will reveal, not fully, and that is the sign of a powerful tool. The best simulations don't just confirm what we expect, they show us things we didn't know we were missing. They lead us down rabbit holes, spark new theories, and open doors to questions no one thought to ask. They might even help us build entirely new branches of science, not by simulating what we already know, but by simulating what we've never dared to imagine. In the years ahead, the boundary between simulation and exploration may blur. We may begin to treat our digital universes as more than just mirrors of reality. They will become canvases, laboratories, partners in discovery, places we go not just to test our understanding, but to expand it. And somewhere, perhaps decades from now, someone will boot up a simulation so detailed, so strange, and so alive with complexity that they'll sit back, blink at the screen, and ask, who's simulating whom? Imagine standing before an enormous canvas. It stretches beyond sight in all directions, a silent tapestry of motion and light. Stars are born and die, galaxies twirl like dancers in the dark, and invisible threads bind everything together with quiet strength. You cannot see the full picture all at once. It is simply too vast. But you can trace its outlines, sketch it gently. Let your pencil hover and draw what you feel, if not what you fully understand. This is what a simulation does. It sketches the cosmos, not with charcoal or ink, but with numbers and rules, with particles and pixels. It does not capture every detail, and it does not pretend to. Instead, it follows the contours of the universe, the way a shadow follows a form. And somehow, in this act of imitation, we come to understand reality not as a fixed photograph, but as a performance always in rehearsal. The beauty of this rehearsal lies in its honesty. A sketch does not lie about its incompleteness. It embraces it. The lines are open to revision. The proportions are guesses. The artist's hand is visible in every stroke. And still, the sketch conveys something true, something that photographs might miss, a suggestion of movement, a whisper of intention, a glimpse of what holds the world together, even if the edges are unfinished. In the same way, simulations help us see what is otherwise hidden. The long, patient growth of galaxies, the dance of dark matter beneath luminous halos, the feedback loops that shape entire star systems. They give motion to what is usually still and structure to what might seem chaotic. They are not the thing itself, but a way to understand the thing, a rehearsal for the real, performed in code. This doesn't mean reality is made of code, it probably isn't, and scientists generally don't think so, but it is responsive to rules. The universe listens to its own logic, the laws of physics, the constants of nature, the strange symmetries that let equations predict eclipses and particle masses with eerie precision. We don't know why those rules exist, or why they work. But we do know that we can play them like music, and play them we do. With each new simulation, we tune the instruments a little more finely. We adjust the gravity, we tweak the chemistry, we vary the initial conditions and let the universe unfold again and again, like a cosmic rehearsal hall echoing with possibility. Some rehearsals are triumphant, others are strange, some look nothing like the universe we know. But even those tell us something about how this all might have been, or might yet become. The elegance of this approach is that it doesn't require perfection. In fact, it thrives on imperfection. A simulation that matches the real universe too precisely might feel impressive, but also suspicious. Where is the noise? Where is the surprise? Real reality is messy, uncooperative, full of the unexpected. Simulations at their best embrace that. They explore the nearby paths, the maybe-could-have-beens, the cosmic adjacent possibilities. Like good sketches, they are never final drafts. And perhaps this is one reason simulations resonate so deeply with us. Because we too are rehearsing. Every moment of being human is a kind of simulation, running mental models of what might happen, testing scenarios in our heads before they unfold in the world. Should I say this? What if I try that? Our brains are not perfect predictors, but they're decent sketch artists. They don't give us certainty, but they offer outlines, and sometimes that's enough to find our way. In that sense, the act of simulating, whether a galaxy or a conversation, is profoundly human. It's a way to prepare, to reflect, to imagine. It's what makes science possible, and empathy, and storytelling. We are creatures who guess before we know, and sketch before we see. Simulations are just an extension of that instinct, elevated by silicon and scale, but born from the same curiosity. Of course, not all sketches are kept. Many are tossed aside. Some are wrong in ways that are immediately obvious, others in ways that take years to discover. But each one leaves a trace, a lesson, an intuition that deepens our understanding of the universe, or ourselves, or both. In that way, nothing is wasted. Even an abandoned model becomes part of the rehearsal. A scene we tried, a line we tested, a moment that shaped what followed. And there is a certain grace in that process. To simulate is to be humble. It is to admit that we do not know, but want to. It is to build something that will surely fall short and build it anyway. Because every approximation brings us closer to insight. Every digital galaxy carries a shadow of the real, and every run of the code is another step in the long, slow dance between imagination and truth. In the end, perhaps the universe is not made of equations, but of the things that make equations meaningful: space, time, matter, and the relationships between them. Simulations do not create those things, but they do help us draw their outlines, like fingers tracing constellations in the dark. They remind us that to understand is not to capture, but to approach, not to possess truth, but to reach for it, gently, with curiosity and care. So we return to the sketch, the canvas still unrolling, the outline still forming. We watch, and we learn, and we run the model again. This time with more resolution, this time with better physics, this time with a different question in mind. And all the while, the real universe continues, unwatched, unsimulated, performing its quiet ballet of expansion and collapse, of formation and decay. It does not care whether we understand it. It does not require rehearsal. But still it allows us to watch, to wonder, and to sketch. And maybe that's enough. At the edge of sleep, with the lights low and the world quiet, it's comforting to imagine the universe not as chaos, but as something we can trace, something with structure, with rhythm, with rules that we're slowly beginning to understand. Not because we're cosmic beings ourselves, but because we're curious ones. We began this journey with a simple question. What does it mean to build a universe? Not to control it, not to design it from scratch, but to model it, to simulate it, to ask, If we understand the ingredients, the particles, the forces, the equations, could we recreate what we see? Could we press play on a digital cosmos and watch it unfurl into something familiar? Along the way, we've seen simulations that do just that. Models that give birth to galaxies, swirl dark matter into filaments, launch stars from swirling clouds, and trace the life cycle of black holes. We've seen universes in boxes and zoom-ins that focus so tightly they capture the delicate formation of a single disk of stars. And yet, with every pixel rendered and every parameter tuned, the truth remains. We are not building the universe itself. We are building ideas, explorations, approximations. Code is not reality, but it is a way to understand reality, a mirror made of logic and light. It's tempting to imagine that these simulations might one day answer all our questions, that if we just add enough resolution, enough physics, enough clever machine learning algorithms, the universe will yield its deeper secrets. But perhaps what makes simulations so powerful is not their accuracy, it's their humility. They teach us where the gaps are. They reveal what we don't yet know. They point toward mystery even as they explain. We asked whether simulations can predict or only reflect, whether they can capture consciousness or merely mimic behavior, whether the very act of modeling the cosmos changes how we see ourselves. And in a sense, the answer is yes to all and no to all. Because the real magic isn't in the models, it's in the questions they provoke. There's a quiet beauty in that, in knowing that even when our models fail, they do so usefully. A broken prediction is not a mistake, it's a doorway. An incorrect outcome is not the end, it's the beginning of a better question. In this way, building a universe becomes less about certainty and more about rehearsal, about listening closely to the code and what it does not yet understand. And maybe that's the point. The universe does not owe us answers, but it allows us to keep asking. It lets us write programs and equations and watch as digital stars flicker to life. It allows us to guess, to refine, and to feel for a moment that we are part of the same quiet logic that keeps galaxies turning. So whether you're drifting to sleep or still wide awake with wonder, remember, simulations are not truth, they are sketches, and sketches matter. They are how we think, how we explore, how we imagine what might be out there, and in here too. In the end, perhaps building a universe is not about assembling pixels or particles. It's about tracing patterns, listening closely, sketching carefully, and seeing in every model not just the stars, but ourselves.